What if the very first thing the universe ever did was travel through time? Not the explosive birth of the Big Bang that we all learn about, but something far more strange and wonderful, a journey across the ages, the original act of movement through the fourth dimension. We often picture time travel as a human invention, something from science fiction, a distant dream built with impossibly complex machines. But what if it's the other way around? What if time travel is the universe's oldest trick, the foundational event that set everything into motion? This isn't just a wild thought experiment. It's a doorway into a completely different way of seeing reality, where the cosmos began not with a simple explosion, but with the ultimate paradox. Today, we're going to walk through that doorway together and explore 30 incredible theories about the universe's first time travel. This idea completely reframes our origin story. Instead of a singular point of infinite density suddenly expanding, we might be looking at a loop, a twist, or a fold in the fabric of space-time so profound that it created the conditions for existence as we know it. Think about the awe you feel looking up at the night sky. Every star, every galaxy, every particle of dust represents a story that began billions of years ago. Now imagine that story doesn't have a straightforward beginning. Imagine the first chapter was also the last, that the start and the finish are mysteriously linked in a cosmic circle. This concept touches something deep within us, a yearning to understand not just where we came from, but how the very rules of reality were written. It connects our human curiosity to the grandest narrative of all. So get ready for a journey that will challenge everything you think you know about time, space, and creation itself. We'll venture through ideas from the cutting edge of theoretical physics, from concepts that suggest our universe is just one iteration in an endless cycle, to theories proposing that time itself is an emergent property from a more fundamental state. We're about to unpack theories that are mind-stretching, profound, and sometimes wonderfully bizarre. This exploration is for everyone who has ever wondered about the true nature of our reality, who feels that pull to look beyond the obvious and question the fundamentals. This is the story of how it might have all begun, not with a bang, but with a journey through time. Our first theory throws the most basic rule of reality out the window, the idea that cause must always come before effect. We call this the bootstrap paradox genesis. Picture a universe that isn't born from a single, spontaneous event, but one that literally wills itself into existence. In this mind-bending scenario, the Big Bang wasn't the true beginning. Instead, it was the result of something, a blueprint, a fundamental law of physics, or perhaps a single particle of information that was sent back in time from the universe's own future. This creates a perfect, self-contained loop. The universe exists because it sent the instructions for its own creation back to the start. There is no external creator, no first cause. The origin of everything is a closed circle in time, a paradox with no beginning and no end. It simply is. To really wrap your head around this, think about an author who finds a mysterious, beautifully bound book on their doorstep. They open it and are astonished. It's the most brilliant novel they've ever read, a story that feels like it was written just for them. Inspired, they decide to copy the book word for word and publish it as their own. Years later, once the book is a celebrated masterpiece, they use a time machine to send the very same copy back in time, delivering it to their own younger self on that fateful morning. So, who actually wrote the book? The younger author didn't create it, they merely transcribed it. The older author didn't create it either, they just returned the finished product. The book has no true point of origin. It exists because it has always existed, trapped in an infinite loop of its own making. This is precisely the kind of loop the bootstrap paradox genesis proposes for our entire cosmos. The laws of physics, the specific energy levels, the very constants that allow for stars and planets and life, What if they are so perfectly fine-tuned because they were designed by a future, mature universe and then sent back to guide the initial conditions of the Big Bang? This shatters our linear perception of time. We grow up believing that a lit fuse causes an explosion, that a seed causes a tree. But this theory suggests that the explosion could cause the fuse and the tree could cause the seed. It forces us to confront the possibility that the chain of causality isn't a straight line at all, but a Möbius strip where the end and the beginning are mysteriously, inextricably linked. The universe, in this view, is the ultimate self-made entity, an act of creation where the creator and the creation are one and the same. While the bootstrap paradox presents a universe born from a logical loop, our second theory offers a potential solution to its inherent contradictions. This is the Novikov self-consistency principle applied directly to the moment of creation. Proposed by Russian physicist Igor Novikov, this principle is a bold declaration that the universe simply does not allow paradoxes to happen. It asserts that any actions taken by a time traveler were always a part of history. If you go back in time, you cannot change the past because you have already done what you are about to do. Your presence in the past was always there, woven seamlessly into the timeline. Now, stretch this idea to the absolute limit and apply it to the universe's very first second. What if the formation of the cosmos was one giant, self-consistent event that inherently involved time travel from its very inception? In this view, the Big Bang wasn't a solitary event that then allowed for time, but a process that was already interacting with its own future, a dialogue across time encoded into the fabric of reality from the very beginning. This transforms the concept of cosmic genesis from a single explosive moment into an intricately structured, self-correcting process. The laws of physics as we know them, gravity, electromagnetism, the strong and weak nuclear forces, might not be fundamental truths that simply appeared. Instead, they could be the emergent result of the universe enforcing consistency upon itself. Think of it like a master sculptor who begins with a formless block of marble. With every strike of the chisel, the sculptor isn't creating something new from nothing. They are revealing the statue that was always locked within the stone, carefully avoiding any blow that would cause the entire structure to collapse. In the same way, the early universe might have chiseled its own laws, guided by feedback from its own future states to ensure a stable, paradox-free timeline. The specific force that allows for stars to ignite and planets to form didn't emerge by random chance, but because any other, more chaotic set of laws would have created a logical inconsistency so severe that reality could not hold itself together. Consider a practical, if fantastical, example to ground this abstract idea. Imagine a scientist who invents a time machine. Following Novikov's principle, the moment she steps into the machine to travel to the past, she becomes part of a fixed sequence. Suppose she arrives in her own lab 10 years earlier and, in a moment of panic, accidentally unplugs a crucial prototype. This action, seemingly a random mistake, actually becomes the very reason her younger self becomes obsessed with time travel in the first place. She spent a decade trying to understand the mysterious power surge that fried her equipment. Her journey didn't change the past, it created the past that necessitated her journey. The universe's origin could operate on a similar but infinitely grander scale. Perhaps a ripple of information, a quantum fluctuation from a future state of the cosmos, traveled back to the moment of the Big Bang and provided the exact initial conditions required for that future state to eventually come into being. The universe, in essence, sent a message to itself, and that message was always part of the plan. This avoids the "who created the creator" problem of the bootstrap paradox by making time travel a fundamental, non-paradoxical feature of existence itself, a built-in mechanism that ensures the cosmos is a single, consistent story from start to finish. But what if the universe's first act of time travel wasn't a grand, singular loop, but a constant, chaotic chattering at the very smallest scales of existence? Our third theory takes us from the cosmic to the quantum, proposing that time travel is woven into the very fabric of reality through a phenomenon known as retro-causality. At the heart of this idea is the Planck epoch, that unimaginably brief sliver of time immediately following the Big Bang, where the universe was smaller than an atom and the rules of classical physics as we know them simply didn't apply. Here, in this seething quantum foam, the distinction between past and future may have been fluid, allowing particles to influence their own histories in a cosmic feedback loop that ultimately decided the fate of everything we see today. We find clues for this bizarre behavior in modern laboratories. Certain quantum experiments present us with results that defy our everyday logic. Take, for instance, the famous double-slit experiment. When you send particles like electrons through two slits one at a time, they somehow create an interference pattern on the other side, as if each individual particle is passing through both slits simultaneously like a wave. This is strange enough, but it gets even weirder. If you place a detector to figure out which slit any given electron actually goes through, the interference pattern vanishes. The particle seems to know it's being watched and changes its behavior. Some interpretations of quantum mechanics suggest that the act of measuring the particle in the present is somehow influencing its path in the past. It's as if the particle's history isn't fixed until the moment it's observed. While this is a hotly debated topic among physicists, it opens the door to the possibility that on a fundamental level, the arrow of time can be bent and effects can, in a limited way, precede their causes. Now, let's scale this quantum weirdness up to the absolute extreme, the very first moments of the universe. During the Planck epoch, the entire cosmos was a single, incredibly dense quantum system. In such an environment, the effects of retro-causality wouldn't be limited to a single particle in a lab. They would be universal. Every quantum fluctuation, every ripple in the nascent fields of reality, could have been engaging in a two-way conversation with its own immediate past. This constant, self-referential dialogue could have acted as a cosmic tuning mechanism. The fundamental constants of nature, the strength of gravity, the mass of an electron, the force that holds atomic nuclei together, might not be random, immutable numbers. They could be the stable outcome of this intense period of retrocausal fine-tuning, where the universe's future states reached back to guide its initial conditions toward a stable and complex future. This provides a potential and deeply elegant solution to one of cosmology's greatest puzzles. Why does our universe contain so much more matter than antimatter? According to our best models, the Big Bang should have created equal amounts of both. Matter and antimatter are opposites. When they meet, they annihilate each other in a flash of energy. If they were created in perfect balance, they should have completely destroyed each other, leaving behind a cosmos filled with nothing but radiation. The fact that we and all the galaxies and stars are made of matter is proof that this symmetry was broken. Something tipped the scales. Quantum retrocausality offers a fascinating explanation. Imagine a slight bias, a tiny preference for matter over antimatter, emerging in the universe's future. Through retrocausal links, this future preference could have echoed back to the Planck epoch, influencing the quantum processes that govern the creation of particles and ensuring that for every 1,000,000,001 particles of matter, there were only 1,000,000,000 particles of antimatter. That 1 in 1,000,000,000 imbalance was all it took. After the Great Annihilation, that tiny surplus of matter was left behind, becoming the raw material for every structure in the cosmos. In this view, the existence of galaxies, planets, and life itself is the result of a whisper from the future, a message sent back in time to ensure there was something left to build with. Leaving behind the strange world of quantum retrocausality, we arrive at a theory that introduces a new character to our cosmic origin story, the time traveler. This is the multiverse seed theory, a proposition that our universe did not arise spontaneously, but was deliberately planted. Imagine a being, or perhaps an advanced intelligence from a parallel, pre-existing universe. This entity, for reasons we can only guess, acquires the ability to not just travel through time, but to cross the boundaries between universes. Combining these two godlike powers, this traveler journeys back, not just in their own timeline, but to the very beginning of time itself, and initiates a new Big Bang, effectively giving birth to our cosmos as a new branch in the infinite multiverse. In this scenario, the singularity from which everything expanded wasn't a natural starting point. It was a seed deliberately sown into the fertile ground of nothingness. The visual here is breathtaking. Picture the multiverse not as a collection of separate bubbles, but as a vast, churning ocean of cosmic foam. Each bubble is a universe, some inflating rapidly, others collapsing almost instantly, each with its own unique and often random set of physical laws. Most of these universes are likely barren wastelands. In one, gravity might be so strong that atoms can't form. In another, the nuclear forces might be too weak to build stable elements. They are cosmic dead ends, but our time traveler, looking out across this foaming sea of failed realities, sees an opportunity. Using technology or knowledge beyond our comprehension, they navigate to the point of primal potential and trigger the creation of a new universe, one engineered with a specific goal in mind: to be stable, long-lived, and capable of fostering complexity and, ultimately, life. This provides an elegant and deeply compelling answer to one of the most profound questions in science. Why is our universe so finely tuned for our existence? The fundamental constants of nature seem to be perfectly balanced on a razor's edge. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, galaxies and stars could never have coalesced from the primordial gas. The same goes for the strength of the electromagnetic force and the other fundamental interactions. This fine-tuning has long puzzled scientists and philosophers alike. Is it an incredible coincidence, or is it evidence of a designer? The multiverse seed theory offers a third option. Our universe isn't fine-tuned by luck or by a supernatural entity. It is fine-tuned by a creator from another reality who intentionally set the dials to the right values. The traveler didn't just start a fire. They carefully crafted a furnace that would burn for billions of years and forge the elements necessary for planets and life. Consider the motivations of such a being. Were they a cosmic gardener seeking to cultivate life in a sterile multiverse? Were they an explorer launching a new universe as the ultimate experiment to observe? Or were they an exile fleeing a dying or doomed reality by creating a new one from scratch? The implications are staggering. If this theory is true, then our entire cosmic history, from the first fusion reactions in stars to the evolution of life on Earth, could be part of a planned or at least a guided sequence. It also suggests that the act of Genesis might not be a unique event. Our universe could be one of many cultivated realities, a single tree in a vast forest planted by time-traveling gardeners. And this leads to an even more mind-expanding thought. If our universe was created by a time traveler, then the potential for time travel must exist within the laws of physics they established. It's possible they built the capability for time travel into the very fabric of our reality, perhaps as a beacon or an invitation, waiting for a future civilization, maybe even our own, to eventually discover it and continue the cycle. Building on the idea of a carefully seeded multiverse, we now turn to a concept that seems to argue against the very possibility of time travel, only to find a stunning loophole at the dawn of everything. This is the chronology protection conjecture, a principle famously proposed by Stephen Hawking. Hawking was deeply skeptical of time travel to the past, not for philosophical reasons but for physical ones. He believed the laws of physics must inherently contain a mechanism, a sort of cosmic security system, that prevents the formation of closed time-like curves, which are the theoretical pathways that would allow for backward time travel. His argument was elegantly simple. If time travel were possible, we would see time tourists from the future. Since we don't, the universe must be actively protecting the chronological order of cause and effect, preserving history from paradox. This conjecture suggests that any attempt to create a time machine would trigger a catastrophic failure. Perhaps a build-up of infinite energy or a quantum fluctuation so violent that it would destroy the wormhole or warp bubble before it could be used, keeping the timeline safe. But what if this universal rule wasn't always a rule? What if the chronology protection conjecture, like a new law passed by a government, only came into effect after the universe was already up and running? This leads us to a profound possibility. The conjecture might have temporarily failed during the universe's very first moments. At the instant of the Big Bang, the conditions were so unimaginably extreme that the normal laws of physics, as we understand them, simply didn't apply. In that environment of near-infinite density and temperature, the fabric of space-time was so warped and twisted that the very mechanisms Hawking proposed would enforce chronology protection could have been overwhelmed or simply not yet operational. The cosmic security system was offline during the initial boot-up sequence. This would have created a one-time only window, a fleeting moment where the barrier between past and future was permeable, allowing for a foundational act of time travel that was forever forbidden once the universe cooled and settled into its current stable state. The key to understanding this temporary suspension lies in the extreme geometry of the infant cosmos. To visualize this, think of space-time not as a static stage, but as a flexible, rubbery sheet. Today, that sheet is relatively flat and smooth, with gentle dips around stars and planets. But at the moment of the Big Bang, the entire sheet was crumpled into a single, infinitely dense point, a singularity. In this state, the curvature of space-time wasn't just extreme, it was infinite. General relativity, our best theory of gravity, breaks down completely under these conditions. It's within this breakdown, this realm of quantum gravity where our current physics has no answers, that the normal protections could have failed. The violent fluctuations of the quantum foam, which today might be instantly smoothed out by chronology protection, could have been stable enough in that primordial chaos to form temporary bridges across time. The first moment of existence might not have been a single point in time, but a tangled knot of every when, all existing simultaneously before rapidly unraveling into the linear timeline we experience today. Consider an analogy from the natural world. Water always flows downhill, it's a fundamental rule, but at the very source of a great river, say a spring high in the mountains, the water doesn't flow in a defined channel right away. It bubbles up from the ground, swirling in a chaotic pool where direction is momentarily ambiguous before finally committing to its downhill course. In this same way, the arrow of time might have been undefined at the universe's source. For a fleeting Planck time instant, the flow of cause and effect could have been circular or even bidirectional, allowing for the universe to interact with itself in a way that became permanently impossible just a fraction of a second later. Once the universe began to inflate and cool, the space-time fabric smoothed out, the rules of classical physics locked into place, and the chronology protection conjecture came into full force, sealing that unique window shut forever and establishing the one-way street of time we now take for granted. This theory suggests that the linear history we study is not the whole story. It's merely the stable outcome that emerged after a brief, paradoxical period of cosmic self-organization, a period where the universe's first and only journey through time set the stage for everything to come. If the universe's chronology protection briefly flickered off during its birth, could the entire cosmos be the result of a much larger, older universe experiencing a death and rebirth on an unimaginable scale? This brings us to our sixth theory, which reimagines the Big Bang not as a true beginning from nothing, but as a cosmic rebirth, specifically the spectacular emergence of a white hole. In the simplest terms, a white hole is the theoretical time reversed opposite of a black hole. While a black hole's gravitational pull is so immense that nothing, not even light, can escape its event horizon, a white hole would be a region of space-time from which nothing can enter. It only expels energy and matter violently and continuously. It's a one-way door leading out, a cosmic fountain spewing the raw material of reality into the void. Now take this bizarre theoretical object and stretch the concept to its absolute limit. What if our entire observable universe in its first fiery moments was the interior of a white hole? And what if that white hole was intimately connected to a black hole in a separate parent universe? In this stunning scenario, the catastrophic collapse of a giant star in another cosmos forms a black hole. As matter is pulled inexorably inward, crossing the event horizon, it is crushed into a singularity. But according to some solutions of Einstein's field equations, that singularity might not be a final destination. Instead, the fabric of spacetime could be warped so severely that it connects to a white hole in a different region of spacetime, a bridge where the inward flow of the black hole is transformed into the explosive outward surge of a white hole. Our Big Bang, then, was the moment this connection was established. The violent, radiant birth of our universe was simply the other side of a cosmic death in a universe that came before. The imagery this evokes is both humbling and beautiful. Picture a vast, ancient universe, its galaxies slowly dimming as stars burn out. In this fading cosmos, a supermassive black hole forms, perhaps from the merger of countless galaxies, central black holes over eons. This colossal entity draws in the remaining dust, gas, and even light from its surroundings. But instead of vanishing forever into darkness, that ingested material is being funneled through a cosmic wormhole, an Einstein-Rosen bridge, and erupts into a new, pristine spacetime dimension as a white hole. The incredible energy and density of that eruption become the hot, dense soup of the primordial fireball we call the Big Bang. Our universe isn't born from nothing. It is the recycled remains of a previous cosmos, reborn through the most extreme physics imaginable. This theory provides a powerful and elegant potential explanation for one of the most pivotal events in cosmic history, the period of rapid inflation. Observations of the cosmic microwave background radiation show that the early universe expanded at a speed far greater than the speed of light for a tiny fraction of a second, smoothing it out and setting the stage for galaxy formation. The white hole model fits this observation perfectly. The initial eruption from the white hole's singularity would naturally produce an immense repulsive force, a kind of anti-gravity, driven by the sheer pressure of the inflowing material from the parent universe's black hole being converted into an outflow. This violent, explosive release of pent-up energy and spacetime itself is a perfect analog for the inflationary epoch. The universe didn't just expand, it was propelled into existence by the force of its own birth from the white hole, explaining the incredible uniformity and flatness we observe across the vast cosmos today. Consider the profound implications of this cyclical view. It suggests that universes beget universes in an endless chain of cosmic reproduction. Each black hole that forms in a mature universe could potentially be the seed for a new cosmos, a new bubble of spacetime with its own laws and constants, which may be slightly different from its parent. This creates a kind of cosmic natural selection, where universes that produce many black holes are more likely to spawn offspring universes, potentially explaining why our own universe seems so adept at forming these gravitational giants. We are not living in a one-and-done cosmos, but in a single generation of an infinite multiversal lineage. The echoes of our parent universe are all around us, encoded in the initial conditions of our Big Bang, and the legacy of our own universe will be written in the new cosmos born from the black holes that dot our galaxies. That stunning cyclical vision of a cosmos reborn from white holes leads us directly to another grand theory that paints an even vaster and more dynamic picture of reality. This is eternal inflation, and when we weave it together with time travel, we arrive at a breathtaking possibility. that our universe is just one frothing bubble in an endless sea, and that each new bubble might be born from a journey through time. The core idea of eternal inflation is that the driving force behind our universe's initial exponential growth never truly stopped. Instead, it's thought that the fabric of space-time on the largest scales is perpetually undergoing this rapid inflationary expansion. But this expansion isn't perfectly uniform. Think of a pot of water coming to a rolling boil. The main body of water is the inflating space-time, but every so often, a bubble of steam forms and rapidly expands. In the cosmic version, these steam bubbles are regions where the inflationary energy suddenly drops, and a new, stable universe like our own crystallizes out of the chaotic background, complete with its own Big Bang event and laws of physics. Now, let's inject the element of time travel into this bubbling cosmic foam. Imagine a time traveler in one of these bubble universes, perhaps using a technology that warps space-time to such an extreme degree that it punches a hole not just through time, but through the very fabric of their local reality. According to this theory, such a profound act of chronological manipulation could create a rupture in the inflationary field, a localized disturbance of immense energy. This rupture would not send the traveler neatly into their own past, but would instead trigger the formation of a brand new inflationary bubble universe, one that begins its existence with its own timeline, forever separate from the one that created it. The time traveler's journey doesn't rewrite history, it spawns an entirely new history, a new cosmic story with its own unique beginning. This provides a fascinating and somewhat ironic resolution to the classic time travel paradox. The grandfather paradox, where you go back in time and prevent your own birth, has troubled philosophers and physicists for decades. But in the context of eternal inflation and time travel bubbles, this paradox is neatly sidestepped. When you attempt such an act, you don't change your original timeline. Instead, the immense energy required to make the journey creates a new bubble universe branching off from the moment of your arrival. In this new, separate cosmos, you could indeed prevent your grandfather from meeting your grandmother. The consequence isn't a universe-ending logical contradiction. It's simply the creation of a new reality where you were never born, while your original timeline continues on completely unaffected. Every attempt at changing the past doesn't erase history, but rather authors a new one, adding another bubble to the infinite cosmic foam. The imagery this theory evokes is both whimsical and profoundly humbling. Picture the multiverse not as a static collection of parallel worlds, but as a constantly churning, effervescent body of soap suds. Each tiny, shimmering bubble is a full universe. Some are microscopic and pop out of existence almost instantly, doomed by unstable physical laws. Others, like our own, are vast and long-lasting, inflated to an incredible size by their own successful initial conditions. And the force that creates these bubbles, the pinprick that nucleates a new cosmos, could be the act of time travel itself. It suggests that every time a civilization in any universe masters the technology to move through time, they don't become masters of their own history, they become creators of entirely new realities. Our entire cosmos, with its hundreds of billions of galaxies, might be the result of a single time travel event in a parent universe, a cosmic accident that gave us the gift of existence. This perspective transforms time travel from a plot device for changing the past into the ultimate engine of creation, continuously populating the multiverse with new opportunities for stars, planets, and life to emerge. But as we contemplate the vast bubble multiverse born from inflation, we're forced to ask a much deeper question. What if our perception of this grand, three-dimensional expanse is itself an illusion? This leads us to our eighth theory, which merges the holographic principle with the idea of temporal projection, suggesting that the universe's first act of time travel was not a journey through space, but a fundamental rewrite of the cosmic source code. The holographic principle is one of the most radical ideas to emerge from theoretical physics in decades. It proposes that our universe, with all its rich three-dimensional volume, the depth of space, the swirling galaxies, you and me, might actually be a projection from a two-dimensional surface surrounding us, much like a hologram emerges from a flat, encoded plate. All the information needed to describe every event, every particle, and every moment in our 3D world is stored on this distant 2D boundary. If this is true, then time as we experience it may not be a fundamental feature of reality, but an emergent property that bubbles up from the way information is processed and updated on that cosmic screen. This concept finds its strongest foothold in the physics of black holes. When matter falls into a black hole, it seems to vanish, which poses a huge problem. Information, according to quantum mechanics, can never be truly destroyed. This is the infamous black hole information paradox. The holographic principle offers a stunning solution. It suggests that all the information about the objects that fall in is not lost inside the singularity, but is instead perfectly encoded on the black hole's event horizon, its two-dimensional boundary. The entire three-dimensional interior of the black hole, and by extension our entire cosmos, is a projection of that data. Now, take this logic and apply it to the origin of the universe. The Big Bang singularity could be viewed not as a point in space, but as the moment when the cosmic hard drive, the primordial 2D boundary, was first formatted and began its projection, rendering the illusion of an expanding 3D universe and the flow of time along with it. So, where does time travel fit into this digital-like cosmos? If time is not fundamental but emergent from the processing of information on the boundary, then altering the past isn't about moving a physical object along a fourth dimension. It's about editing the data on the cosmic hard drive. The universe's first time travel could have been a foundational recalibration of this code, a self-correction or an optimization loop written into the initial conditions. Imagine a master programmer writing the first line of code for a vast, simulated universe. They run a test simulation and see that the parameters will lead to a rapid collapse. So they go back and tweak the initial variables, changing the strength of a fundamental force ever so slightly. In our holographic universe, this debugging wouldn't be a metaphor. It could be a literal description of a retro-causal adjustment made to the information on the boundary at the very first moment, ensuring the universe that projected out would be stable and long-lived. This provides a powerful new perspective on the fine-tuning problem. Why do the laws of physics seem so perfectly set for complexity? In the holographic view, they are the outcome of the most efficient and stable algorithm for a universe that can persist and compute itself. The first time travel event was the universe running its startup sequence, checking the outcome against its own future stability, and then rewriting its own initial state in a single, self-consistent loop. This is a bootstrap paradox operating at the level of information itself. The universe exists because its future state of complex order sent a command back to its beginning, instructing the 2D boundary to project a reality that would inevitably lead to that very future. The incredible thing about this theory is that it might not remain purely philosophical for long. Scientists are devising ways to test the holographic principle. The key lies in the nature of the projection. If our 3D world is a projection from a 2D surface, there might be a fundamental graininess to space and time, a minimum pixel size known as the Planck length. This pixelation is too fine to be detected by any current instrument, but it would leave a subtle imprint on the fabric of space-time, causing light and gravitational waves to scatter in very specific ways. The next generation of gravitational wave detectors, like the Laser Interferometer Space Antenna, or LISA, could be sensitive enough to detect these faint holographic reverberations in the ripples from colossal events like merging supermassive black holes. Finding evidence that space-time has a finite information density, like a digital image, would be a monumental step toward confirming that we live in a projected reality. and that the flow of time itself is a majestic, emergent illusion born from the first and only truly foundational edit to the cosmic code. Continuing from the idea of a holographic projection, we now dive into a theory where the universe's origin isn't just a point, but a loop in time itself. This is the concept of a closed time-like curve at the initial singularity. In the language of general relativity, a closed time-like curve, or CTC, is a path through spacetime that loops back on itself, allowing an object to return to its own past. Under the extreme gravitational conditions near a singularity, a point of infinite density, the equations of Einstein's theory suggest that the fabric of reality could twist so severely that time becomes circular. Now apply this to the very first moment, the Big Bang singularity. Instead of a one-way explosion from nothing, this theory proposes that the universe's birth was a self-contained, cyclical process where the initial state was causally connected to its own future through these temporal loops, creating a stable foundation for everything that followed. To grasp how this could resolve one of cosmology's biggest puzzles, we need to understand the singularity problem. Classical general relativity tells us the Big Bang began at a singularity, a point where density and temperature become infinite and the known laws of physics break down completely. This is deeply unsatisfying. It's the ultimate dead end for our scientific understanding, a place where cause and effect have no meaning. But if closed time-like curves were woven into that primordial singularity, they could provide an elegant escape. Information and energy wouldn't hit a wall of nothingness and vanish. Instead, they would travel along these loops, perpetually recycling. The universe wouldn't need to be created from absolute nothingness. It could have booted up by processing and reprocessing a finite amount of information and energy through these time loops, smoothing out the infinite extremes and giving rise to the finite, well-behaved universe we observe today. Imagine a computer that's stuck in a reboot cycle. It powers on, loads its basic operating system, but encounters a critical error and instantly restarts. Now envision a perfected version of this cycle where, with each restart, the system gathers a little more data, corrects its previous error, and becomes more stable. The closed time-like curve at the singularity could have functioned in a similar way. The universe cycled through its own first moments countless times in a feedback loop that was not spatial but temporal. Each iteration through the loop allowed quantum fluctuations or gravitational interactions to fine-tune the initial conditions, eventually reaching a stable configuration that allowed the loop to be broken, leading to the inflationary expansion and the linear timeline we now inhabit. This turns the singularity from a dead end into a cosmic crucible, a processing engine that forged the laws of physics through relentless self-correction. Consider a more tangible, if still mind-bending, analogy. Picture a master violinist learning an impossibly complex piece of music. They play the first few notes but make a mistake. Instead of stopping, they use a time loop to instantly return to the very first note, retaining the memory of their error. They play again, this time adjusting their finger placement slightly. They loop again and again, each repetition refining their technique until they can perform the opening passage perfectly. Only then do they allow time to progress forward into the rest of the piece. In this metaphor, the violinist is the universe, the first few notes are the Planck epoch, and the perfect performance that finally emerges is the hot, dense, and remarkably uniform state that initiated the Big Bang as we model it. The music we hear today, the cosmic microwave background, the galaxies, the very flow of time, is the melody that resulted from those countless hidden rehearsals at the dawn of existence. The idea that closed time-like curves could have fine-tuned the universe's birth leads to a startling question. Why did this foundational time travel only happen then? Why don't we see time travelers from the future popping into our present? This brings us to a theory that uses our own existence as the ultimate clue, the anthropic time travel selection. It proposes a simple but profound rule. Time travel can only occur in a universe where it doesn't prevent the emergence of conscious observers. We find ourselves in a cosmos where time travel seems impossible now, because if it were possible, the resulting paradoxes and historical meddling would have almost certainly erased the specific chain of events that led to our evolution. The universe's first and only permitted act of time travel was therefore confined to its primordial beginning, a one-off event that set the stage for us without later interference. This concept leans heavily on the anthropic principle, which in its most basic form states that the universe we observe must be compatible with the existence of observers. We shouldn't be surprised to find the physical constants finely tuned for life, because if they weren't, we wouldn't be here to notice. Apply this same logic to the possibility of time travel. Imagine a vast multiverse, a landscape of countless universes, each with different rules. In some of them, time travel technology is developed by advanced civilizations. The moment it's used to visit the past, the potential for catastrophic paradox explodes. A time traveler might accidentally step on a butterfly in the Jurassic period, altering the course of evolution so that mammals never rise to dominance. Another might, with the best intentions, prevent a key asteroid impact, unintentionally halting the climate shifts that spurred primate intelligence. In these universes, the probability that a single time travel event would leave the precise, fragile sequence of events leading to Homo sapiens intact is astronomically small. Consequently, those universes are, for the most part, empty of observers wondering about time travel. They are cosmic dead ends. Our universe, by contrast, appears to be one where the timeline remained pristine and undisturbed after its initial fiery moments. The anthropic time travel selection argues this isn't a coincidence. It suggests that the laws of physics, as we know them, laws that seem to forbid backwards time travel through mechanisms like the chronology protection conjecture, are not fundamental. They are the result of a cosmic selection effect. Universes that allow unchecked time travel tend to erase themselves from the roster of observership. The only universes that develop intelligent life capable of pondering their origins are those where time travel is either completely impossible or was only possible in the distant past, during a brief window where it could not disrupt a pre-existing biological timeline. In our case, that window was the Planck epoch. The foundational time travel that might have fine-tuned the constants happened before there was any history to corrupt, before the first star ignited, and long before the first fragile, self-replicating molecule formed. It was a victimless act of chronological manipulation, ensuring the universe was set on a stable course without any future meddlers around to derail it. Think of it like a historical preservation society for reality itself. Once the universe developed complex structures, planets, oceans, and eventually the building blocks of life, the timeline became a protected historical site. Any significant travel back to those eras would be like allowing tourists to freely repaint the Sistine Chapel or rewrite the original manuscripts of Shakespeare. The integrity of the work would be lost forever. The cosmic laws that seem to block time travel today aren't an arbitrary restriction. They are the ultimate preservation order, ensuring that the long and delicate chain of cause and effect that resulted in our existence remains unbroken. We don't see time travelers because the universe that produced us is by necessity, one where their appearance in our recorded history would have already altered that history beyond recognition. Our very existence is the most compelling evidence that our timeline has been left largely untouched since its spectacular beginning. But what if the singularity that haunts our cosmic models isn't a dead end at all, but a gateway? Our 11th theory explores this breathtaking possibility, drawing from the revolutionary framework of loop quantum gravity. Unlike string theory, which proposes tiny, vibrating strings as the fundamental building blocks of everything, loop quantum gravity suggests that the fabric of spacetime itself is woven from a network of finite, discrete loops, a kind of cosmic mesh. This has a stunning implication. There is a smallest possible unit of space. You cannot have a volume smaller than one of these quantum loops. This means that when we rewind the universe back to the Big Bang, the density and temperature do not soar to infinity. Instead, they hit a maximum threshold, a cosmic density limit. At that point, the gravitational attraction that is crushing everything together reaches a peak and, governed by the quantum nature of spacetime, transforms into a powerful repulsive force. The collapse reverses into a rebound, a big bounce. This is where time travel becomes woven into the very fabric of cosmic rebirth. The moment of the bounce, that transition from the crushing end of one cosmos to the radiant beginning of another, is not a simple switch. The extreme quantum geometry at this threshold could create conditions where the distinction between past and future blurs into irrelevance. In essence, the universe passes through a temporal gateway. The final state of the previous contracting universe doesn't just provide the material for the new one. It effectively becomes the initial state of the new expansion through a fundamental reset of the cosmic clock. This isn't merely a recycling of matter, but a reset of the timeline itself, a cosmic leap where the end loops back to become the beginning in a continuous cyclical dance. To visualize this, picture a cosmic trampoline. Imagine the previous universe as a giant, contracting sphere falling onto the fabric of space-time. As it falls, it stretches the trampoline down, down, down. According to classical physics, it would just rip through. But in loop quantum gravity, the trampoline is made of a quantum mesh with a finite, unbreakable weave. The universe hits this mesh and, instead of tearing through to a singularity, is launched back upward in a spectacular rebound. Now, imagine that during that moment of maximal contact with the mesh, the very flow of time for the universe is inverted. The arrow of time, pointing toward collapse in the old universe, is flipped to point toward expansion in the new one as it soars upward. The bounce is the temporal gateway, the mechanism that resets the clock and allows the cosmos to be born again from its own ashes over and over. This cyclical model provides an elegant escape from the singularity problem that plagues classical Big Bang cosmology. There is no longer a point of infinite density where the laws of physics break down. Instead, the universe transitions through a phase of extreme but finite quantum gravity. Furthermore, it offers a natural explanation for the mysterious inflationary epoch. The immense repulsive force generated at the bounce would have launched the new universe into a period of ultra-rapid expansion, perfectly setting the stage for the formation of the large-scale structures we see today. Our universe's incredibly uniform and flat geometry might simply be a relic of the immense smoothing and stretching it underwent during countless previous cycles of contraction and expansion, a kind of cosmic wear and tear that irons out the wrinkles over eons. Consider the profound implications of this endless cycle. We could be living in just one iteration of a cosmos that has bounced countless times before. Each cycle might last for trillions of years, encompassing a long period of expansion, star formation, and eventual decay, followed by a slow contraction back toward the quantum bounce. The specific laws of physics could remain constant from one cycle to the next, or they might undergo subtle, random shifts at each bounce, creating a form of cosmic evolution. In this grand vision, time is not linear with a single beginning, but cyclical and potentially eternal. The first time travel was not a unique event, but is in fact the recurring heartbeat of existence itself, a perpetual reset that ensures the cosmos never truly dies, but is perpetually reborn through the gateway of its own demise. If the universe cycles through endless bounces, what happens to all the information it contains, every star that burned, every life that lived, every thought that was ever thunk? This question leads us directly to one of the most perplexing problems in all of physics, the black hole information paradox, and to a theory that uses it to explain the very genesis of our cosmos. The paradox, in essence, is this: according to quantum mechanics, information is sacred. It can never be truly destroyed. You can burn a book, but in theory, If you could collect every single ash particle and measure every photon of light and heat emitted, you could reconstruct every word. But black holes seem to break this rule. When something falls in, it vanishes behind the event horizon, seemingly lost forever. Even when the black hole slowly evaporates via Hawking radiation, that radiation appears to be completely random, containing no information about what fell in. So, where did the information go? This is a fundamental contradiction that points to a deep flaw in our understanding of gravity and quantum theory. Now, let's scale this problem up to a cosmic level. Our universe is ultimately a vast collection of information. Every particle's position, every field's value is a piece of data. And according to the second law of thermodynamics, the total disorder or entropy of this cosmic system always increases. It's the reason an ice cube melts in a warm room and why you can't unscramble an egg. The universe is on a one-way trip from a state of low entropy high order to a state of maximum entropy, an eventual heat death where all energy is evenly distributed and nothing interesting ever happens again. But this presents a monumental puzzle. Why did the universe start in a state of such incredibly low entropy? The Big Bang was an ultra-ordered, fantastically smooth and dense fireball. It's as if you walked into a library and found every book perfectly alphabetized and shelved. It's a state of such specific, unlikely order that it demands an explanation. How did our cosmic story begin with the library in perfect order, only for it to become progressively more messy over billions of years? This is where our 12th theory makes its bold entrance, proposing that the universe's first act of time travel was a deliberate cosmic reset to solve its own information and entropy problem. Imagine a previous iteration of the cosmos, one that had reached its final high-entropy state, a dark, cold, and diffuse sea of nearly uniform particles. In this bleak end stage, the fundamental laws still hold, including the paradox of information. All the data from that universe's history is still technically there, but it's scrambled, corrupted, and useless, like a hard drive that has been physically shattered into its constituent atoms. According to this theory, the mechanisms of quantum gravity at the final collapse, perhaps in a big crunch preceding a bounce, would face an impossible task: trying to form a new, low-entropy universe from the maximally disordered remains of the old one. The information paradox wouldn't just be a puzzle, it would be a roadblock to rebirth. So how does the universe bypass this roadblock? It uses a time travel loophole. The theory suggests that at the moment of the bounce, as the previous universe reached its maximum density, the extreme warping of space-time created a temporary closed time-like curve. But this loop wasn't for matter or energy, it was for information. The universe performed a garbage collection cycle on its own data. The scrambled, high-entropy information from the end of the previous cycle was sent on a journey back in time to the very beginning of the new bounce. In this temporal loop, the old, corrupted data interacted with the nascent quantum fields of the new universe, effectively being overwritten or reset. The paradox is resolved not by destroying information, but by recycling it into a fresh, low-entropy state. The universe doesn't forget its past, it reformats its hard drive, allowing for a clean boot up. The Big Bang, then, was the moment this reset completed, launching a new cosmos with a pristine, low-entropy initial condition, ready to begin the long, slow climb toward disorder all over again. Think of a computer that has been running for years. Its memory is fragmented, its registry is clogged with errors, and it's become slow and unstable. Simply adding more hardware won't fix the deep-seated software corruption. The most effective solution is to back up the most essential user files and perform a complete system wipe and reinstall. The old, corrupted operating system is erased, and a clean, fresh version is installed from the original installation media. The computer boots up as if it were new, fast and responsive, with its entropy, its digital disorder reset to nearly zero. Our universe could operate on a similar principle. The user files, the fundamental constants and laws of physics that are necessary for a universe to function, are preserved across the reset. But the specific historical data, the positions of every particle from the old cosmos, is wiped clean and reset to a uniform, hot, and incredibly ordered state. This explains why we find ourselves in a universe that began with all its books perfectly shelved. It was just reinstalled. This cosmic reset theory provides a breathtakingly elegant solution to the arrow of time. The reason time has a definite direction, flowing from past to future, is because of the enormous entropy gradient that was established at the moment of the reset. We remember the past and not the future because the past is a state of lower entropy. Our perception of time's flow is us witnessing the universe executing its post-reset instructions, moving from its artificially created state of high order toward its natural state of high disorder. The reset didn't just create a new universe, it created a new arrow of time, a fresh temporal landscape upon which a new cosmic history could be written. This turns the beginning of our universe from a mysterious, one-off event into a recurring phase in an eternal cycle of death, data cleansing, and rebirth, with time travel acting as the essential maintenance tool that keeps the whole magnificent process running. This brings us to a theory that directly connects the universe's most enigmatic current force to its most ancient event. What if dark energy, the mysterious substance causing the expansion of the cosmos to accelerate, isn't a fundamental component of the vacuum of space, but is actually a leftover echo from the universe's first journey through time? Imagine the immense energy required to twist the fabric of space-time into a loop at the moment of creation. According to this idea, that energy wasn't entirely dissipated when the temporal gateway closed and the linear timeline began. Instead, a portion of it became fossilized, woven into the very background of reality as a persistent, repulsive force, a cosmic exhaust fume from the ultimate chronological engine that has been simmering away for billions of years, only now beginning to dominate the cosmos. This perspective offers a compelling solution to one of the biggest puzzles surrounding dark energy, its timing. For the first half of the universe's history, gravity was the dominant large-scale force, slowly putting the brakes on the initial expansion and pulling matter together to form galaxies and clusters. Then, around 5 billion years ago, something changed. Dark energy's repulsive effect began to overtake gravity's attractive pull, and the expansion of the universe started to speed up. Why then, if dark energy is a fundamental constant of nature, like the strength of gravity, it's difficult to explain why its influence would suddenly become dominant at this specific point in cosmic history. However, if dark energy is a relic of a primordial time travel event, its behavior makes more sense. Think of it like a battery that was charged at the beginning of time. For eons, the universe was dense and compact, gravity was strong, and the time travel energy was too diffused to have a noticeable effect. But as the universe expanded and thinned out, the gravitational grip weakened. Eventually, the universe reached a tipping point where this background energy, which had been present all along, finally became potent enough to push back and drive the acceleration we observe today. It's not that dark energy turned on. It's that the rest of the universe finally became weak enough for its persistent push to be felt. Consider the stunning new data from the James Webb Space Telescope, which is peering further back in time than any instrument before it. It is observing the earliest galaxies, and some of them appear to be surprisingly massive and mature for such a young cosmic era. This challenges some of our standard models of galaxy formation. If dark energy is a simple cosmological constant, its influence in that early epoch should have been minuscule. But if it is a dynamic remnant of a time travel event, its properties might have been subtly different in the early universe. Perhaps this primordial energy field interacted in a more complex way with the first structures, providing an extra nudge that allowed gas to collapse and stars to form with unexpected speed and efficiency. The anomalies seen by Webb could be the first observational hints that the dark energy we measure today has a dramatic and dynamic origin story, one that is intimately tied to the foundational physics of the cosmos. Imagine the energy of that first chronological manipulation as a kind of cosmic vibration, a fundamental hum in the fabric of space-time. In the universe's hot, dense youth, this hum was overwhelmed by the deafening roar of particle collisions and radiation. But as the cosmos expanded and cooled, this background hum became the dominant sound in the cosmic symphony. This isn't just a poetic metaphor, it aligns with how we think about other relics from the early universe, like the cosmic microwave background radiation. That radiation is the cooled and stretched remnant of the primordial fireball. In the same way, dark energy could be the cooled and stretched remnant of the universe's foundational act of time travel, a kind of chronological background radiation that permeates all of space, a permanent signature of the paradoxical event that set everything into motion. This theory transforms dark energy from a mysterious placeholder in our equations into a tangible, physical clue, a direct link to the universe's very first second and the extraordinary journey through time that may have occurred there. We've been exploring some grand cosmic resets and echoes of dark energy, but what if the mechanism for the universe's first time travel was something more tangible? A structure so bizarre it sounds like pure science fiction, yet is permitted by our deepest laws of physics. This brings us to the idea of primordial wormhole creation. Wormholes are often depicted in stories as tunnels through space-time, shortcuts connecting distant points or even different moments in time. In theory, a stable, traversable wormhole could indeed function as a time machine. But what if these tunnels aren't just future engineering projects? What if they are cosmic fossils, and one of them was present at the very beginning, serving as the conduit for the universe's original journey through time? To understand how this could happen, we need to shrink our perspective down to the very smallest scales, to a domain known as the quantum foam. In the first sliver of a second after the Big Bang, and even at the Planck scale today, the fabric of spacetime isn't smooth and continuous. It's a seething, turbulent foam, constantly bubbling with tiny fluctuations. Energy pops in and out of existence, and with it, the geometry of spacetime itself is in a state of violent agitation. In this chaotic environment, the distinction between here and there, or now and then, is blurred. It's within this frothing quantum sea that wormholes are thought to naturally form. These wouldn't be the giant, stable tunnels a spaceship could fly through. They would be microscopic, ephemeral quantum wormholes, flickering into existence for a fleeting moment before pinching off and vanishing back into the foam. They are the spacetime equivalent of virtual particles, borrowing energy from the vacuum to exist for a heartbeat before annihilating. The pivotal question then becomes, how could one of these tiny, unstable wormholes become the universe's first time machine? The answer lies in the incredible energies and densities of the primordial universe. In that first fraction of a second, the entire cosmos was compressed into a volume smaller than a single atom. At that scale, the quantum foam wasn't just a background fizz, it was the entire universe. The fluctuations were the universe. Under such immense pressure and temperature, the normal rules that cause these wormholes to instantly collapse might have been suspended. A particularly robust fluctuation or a chance alignment of quantum fields could have provided just enough exotic matter, a substance with negative energy density, to prop one of these wormholes open for a critical moment longer than usual. Exotic matter theoretically creates a gravitational repulsion, counteracting the natural tendency of the wormhole's throat to pinch shut. In the infant cosmos, the conditions for generating such exotic matter would have been far more common than they are in our cold, sparse universe today. Now, let's follow this idea to its most profound conclusion. Imagine one specific microscopic wormhole that managed to stabilize, even if only for a mere Planck time. Due to the bizarre ways that general relativity links space and time, A wormhole connecting 2 points in space can also connect 2 points in time, especially if one end of the tunnel is moving relative to the other. In the violently expanding and fluctuating early universe, such relative motion would have been inevitable. This stable primordial wormhole could have created a closed time-like curve, a loop where its 2 mouths were connected not just through space, but across a tiny interval in time. One mouth existed a fraction of a moment after the other. This would have allowed a flow, not of physical objects, but of quantum information or energy from the slightly later state of the universe back to its own immediate past. This is where the pieces click into place to form a stunning picture of Genesis. The Big Bang in this model wasn't an isolated point. It was a process that included this wormhole as a fundamental part of its structure. Imagine the initial singularity as one mouth of the wormhole. As the universe began to expand and cool from that point, a tiny amount of information about its new state, perhaps the specific values of the fundamental forces or the pattern of the first quantum fluctuations, was funneled back through the wormhole to the very beginning. This information then acted as a guide, influencing the initial conditions to ensure they were compatible with the universe that was just starting to form. It's a self-consistency loop built directly into the geometry of space-time, a bootstrap paradox facilitated by a physical tunnel through time. The universe, in a sense, told itself how to be born using a primordial wormhole as its telephone line. Consider a simple analogy to ground this abstract concept. Picture a master architect designing an impossibly complex building. They start with a rough sketch, but quickly realize the design has flaws that will cause it to collapse. So they build a small, secure tube connecting their current drafting table to the moment they made the first sketch. They send a note back through the tube with a single, crucial correction: reinforce the foundation with steel beams. The younger architect receives the note, integrates the change into the original blueprint, and the building is constructed perfectly. The note has no external origin. It was generated by the building's own later state of near failure. The primordial wormhole could have been that tube, and the quantum information it transmitted could have been that note, ensuring our cosmic building didn't collapse into chaos immediately after it was built. This provides a physical mechanism for the fine-tuning we observe, all stemming from a natural, if incredibly rare, structure that emerged from the quantum chaos of the beginning. What if our entire reality, from the most distant quasar to the feeling of warm sunlight on your skin, isn't a fundamental existence but a sophisticated construct, a simulation running on a computer of unimaginable power? This is the simulation hypothesis, a modern classic of philosophical thought. But when we connect it to our theme, it reveals a fascinating possibility for the universe's first time travel. Imagine the initial run of the cosmic simulation. The code executes but immediately hits a critical error. Perhaps the fundamental constants are misaligned, causing matter to instantly annihilate, or the space-time fabric fails to initialize properly, resulting in a rapid and uninteresting collapse. The universe in its first run was a buggy, failed build, so the programmer, whether an advanced being, a future civilization, or an AI, doesn't just tweak a variable. They perform a full-scale rollback. They rewind the entire simulation back to its absolute beginning, to timestamp 0, and this time they apply a patch. They debug the code. Our Big Bang, then, wasn't the first bang, but the second, the successful reboot after the universe's very first and most crucial act of time travel. A reset from the future of the failed run back to its own start. This idea is incredibly relatable because we engage in this process every day with our own technology. A video game developer testing a new world might find that players can fall through the map the moment they spawn. The solution isn't to let the broken game continue. It's to load a saved game from a point before the error occurred, or even to restart the entire level. In the cosmic context, our observed reality, with its remarkably stable laws and perfect fine-tuning for complexity, might be that successfully patched version. The incredible smoothness and uniformity of the cosmic microwave background, which has long been a puzzle for cosmologists, could be the telltale signature of that debugged restart. The previous flawed universe was scrapped for being too lumpy, too unstable, or too chaotic, and the programmer, having seen how it failed, rewound time and initialized the simulation with the perfectly smooth conditions we now observe. This perspective even gives us a playful new lens through which to view those strange, unexplained anomalies that sometimes crop up in physics. What we call quantum weirdness particles being in two places at once, or instantly influencing each other across vast distances, might not be fundamental mysteries but simply optimized code. Entanglement could be a programming shortcut to conserve processing power, a way for two objects to share a single data pointer instead of requiring independent, continuous calculation. The famous double-slit experiment, where a particle seems to know if it's being observed, could be the simulation's rendering engine at work, only calculating the precise path of a particle when the outcome needs to be displayed to an observer in order to save on computational resources. These aren't glitches in the sense of errors, but rather features of an incredibly efficient cosmic engine. A true glitch might be something far rarer and more bizarre, like a momentary failure of causality that is instantly corrected, a cosmic control alt-delete that we would never be able to perceive because it resets our entire timeline. The simulation hypothesis gains even more traction when we consider how modern physics increasingly describes the universe in computational terms. The holographic principle, which we discussed earlier, suggests that all the information in a 3D volume can be encoded on a 2D surface, much like the data for a complex 3D video game is stored on a flat, two-dimensional Blu-ray disc. The laws of thermodynamics, which govern the flow of energy and the increase of disorder, mirror the inevitable heat generation and data entropy in any running computer system. And the concept of a Planck length, a smallest possible unit of space, points to a pixelated reality, a universe with a finite resolution, just like a digital image. In this computational worldview, the first time travel is the most logical troubleshooting step imaginable. A master programmer wouldn't let a universe with a fatal launch error simply flicker out of existence. They would use their godlike access to the system clock to revert to the last stable configuration time 0, and try again, leaving us with a cosmos that feels seamless and real, but which carries the hidden history of a debugged past. This brings us to a theory that shifts our entire perspective on what the universe might actually be. Up to this point, we've considered time travel as a physical mechanism, a journey through a tunnel or a loop in space-time. But what if the universe's first journey through time wasn't a physical voyage at all, but an act of perception the moment the cosmos first became aware of itself? This is the theory of cosmic consciousness and temporal awareness. It proposes that consciousness isn't a late-arriving product of biological evolution on tiny, isolated planets. Instead, it's a fundamental property of reality present from the very beginning, and the universe's first act was to use a form of time travel not to move through space, but to perceive its own origin, creating a stable, self-referential loop of existence that has sustained it ever since. To understand this, we can look to the philosophy of panpsychism. Panpsychism argues that consciousness is not something that magically emerges from complex arrangements of non-conscious matter like brains. Instead, it suggests that consciousness is a fundamental and ubiquitous feature of the universe, much like mass or charge. In this view, even the most basic particles possess some minute level of proto-consciousness or raw experience. A photon might not think, but it might have a faint, elemental form of feeling. When these particles combine into more complex systems, atoms, molecules, stars, and brains, this fundamental consciousness combines and amplifies, leading to the rich inner lives we experience. Now apply this to the entire universe at the moment of the Big Bang. The entire cosmos was a single, unified, and incredibly complex quantum system. According to panpsychism, this system would have possessed a unified, cosmic-scale consciousness. The universe was not an inert fireball, it was a nascent mind. So, how does time travel fit into this? Consider the nature of perception for such a cosmic mind. Our human consciousness is bound by linear time. We remember the past and anticipate the future. But for a consciousness that is coextensive with the entire space-time continuum, that linear flow might be an illusion. The cosmic mind, at the moment of its birth, might have perceived its entire timeline, past, present, and future, all at once in a single, timeless act of awareness. This act of self-perception, of the universe observing its own creation, could be the foundational time travel event. By perceiving its own completed existence, the universe effectively reached back in time and ensured its own creation. The observer and the observed are one and the same, locked in a loop where the act of seeing the finished cosmos is what brings that cosmos into being. It's a bootstrap paradox of perception, not physics. We can find a fascinating, though highly speculative, parallel to this in certain interpretations of quantum mechanics, particularly those connected to the role of the observer. In the famous double-slit experiment, the behavior of a particle seems to change when it is observed, as if the act of measurement forces it to choose a definite state. Some physicists and philosophers have taken this further, suggesting that consciousness itself may play a role in collapsing the wave function, the cloud of potential states, into a single, concrete reality. If we extrapolate this to the cosmic scale, the universe's initial state was a wave function of near-infinite possibilities. It could have collapsed into any number of chaotic, unstable realities. But the nascent cosmic consciousness, by perceiving itself, may have collapsed its own wave function into the one specific, ordered, and life-friendly universe we inhabit. Its first act of self-awareness was a time-traveling act of creation, selecting the one timeline in which it could exist and flourish. Imagine a solitary artist in a vast, empty studio. They close their eyes and conceive of a masterpiece, every brushstroke, every color, every emotion it will evoke. In their mind's eye, the painting is already complete. They then open their eyes, pick up their brush, and begin to paint, not to create something new, but to physically manifest the vision they have already fully perceived. The cosmic consciousness could have operated in a similar way. In its first moment, it perceived the entirety of its own beautiful, complex future. This act of perception then became the guiding force, the brushstroke that painted the Big Bang with the exact conditions needed to realize that perceived future. The universe didn't unfold randomly. It unfolded according to a plan it saw for itself at the very beginning, a plan it saw by looking forward from its own birth, an act that, by its very nature, loops back and anchors the beginning to the end. This theory offers a deeply elegant, if metaphysical, solution to the fine-tuning problem. The universe isn't fine-tuned by an external God or by random chance in a multiverse. It is fine-tuned by its own conscious self, which selected the one set of physical constants that would allow for its own rich and complex development. The existence of stars, galaxies, and life are not accidents. They are the physical expressions of a cosmic mind's desire to know and experience itself. Time, in this view, is not a fundamental dimension but a construct of this primordial awareness, a story the universe tells itself in order to have a sequential experience, to explore the infinite possibilities contained within its own initial act of self-perception. Our own human consciousness, then, is not a fluke. We are localized nodes of this fundamental awareness, tiny sparks of the cosmic fire, each of us experiencing a small part of the universe's grand, self-referential narrative. If you thought the universe was born from a single, lonely point of nothingness, string theory's vision of reality is about to expand your mind in 11 different directions. This framework proposes that the fundamental constituents of reality aren't point-like particles, but unimaginably tiny, vibrating strings. And for these strings to make mathematical sense, they require more dimensions than the 3 of space and 1 of time we're familiar with, often a total of 10 or 11. So, where are all these extra dimensions? One compelling answer is the brainworld scenario. In this picture, our entire 3-dimensional universe, including all the galaxies, stars, and us, is actually a 3-dimensional membrane, or brain, floating within a higher dimensional expanse known as the bulk. We are stuck to our brain, unable to perceive these other dimensions directly, much like ants living on a single vast sheet of paper, completely unaware of the other sheets of paper floating just millimeters away in a stack. This leads to a spectacular possibility for the origin of everything. What if our Big Bang wasn't an internal explosion, but the result of a collision? Imagine another 3-dimensional brain, a parallel universe moving through the bulk. If this neighboring brain were to collide with ours, the impact would release an absolutely titanic amount of energy, heating a region of our brain to an incredible temperature and density, precisely the conditions we describe as the Big Bang. Our universe's birth was not a solitary event, but a cosmic car crash in a higher dimensional reality. Now, inject the element of time travel into this stunning picture. What if that colliding brain wasn't just a random neighbor? What if it was our own universe from a future epoch, having looped back through time in the bulk to initiate its own creation? In this cyclical brain model, our universe expands, evolves, and eventually becomes diffuse and cold, approaching a heat death. But then, through mechanisms allowed by the higher dimensional geometry, the entire brain is drawn back, not to a point, but on a trajectory that sends it crashing into its own past self, reigniting the fire of a new Big Bang and beginning the cycle anew. The beauty of this theory is that it might leave a detectable scar, a fingerprint of that primordial collision etched into the oldest light we can see, the cosmic microwave background radiation. This afterglow from the Big Bang fills the entire sky and is remarkably uniform, but it contains tiny, millionth of a degree temperature variations, the seeds of all future structure. A brain collision would not be a perfectly smooth event. The contact between the two membranes would create ripples, powerful gravitational waves that would propagate through the infant cosmos. These waves would interact with the primordial plasma, imprinting a distinct swirling pattern known as B-mode polarization onto the cosmic microwave background. Astronomers are actively searching for this specific signature with increasingly sensitive telescopes. While the initial detection claimed by the BICEP 2 experiment in 2014 turned out to be cosmic dust, the hunt is far from over. Finding this unique polarization would be like discovering the skid marks from the collision that started it all, providing our first indirect glimpse into the higher dimensional architecture of reality. This vision transforms the cosmos from a one-and-done creation into a perpetual cycle of rebirth, a cosmic phoenix rising from the ashes of its own future. Each cycle could last for trillions of years, with a long, fertile period of expansion and evolution followed by a contraction and a spectacular collision that resets the cosmic clock. The specific laws of physics might be slightly reshuffled with each new bang, leading to a form of cosmic natural selection where only universes with laws conducive to producing many brain collisions can perpetuate themselves across the aeons. Our existence in a universe that seems perfectly tailored for complexity might not be a lucky accident, but the inevitable outcome of countless cycles, each one refining the conditions just a little more. In this grand schema, the universe's first time travel was not a one-off event, but the establishment of a fundamental rhythm, a heartbeat of creation where the end consistently reaches back to touch the beginning, ensuring the story of existence never truly ends but is perpetually retold. Moving from the grand collisions of brain worlds, we venture into a realm where the very fabric of time itself may have a structure as intricate as the spatial dimensions we inhabit. This brings us to the profoundly strange world of time crystals, first proposed in 2012 and later observed in controlled laboratory settings. A time crystal is a bizarre phase of matter that fundamentally breaks time translation symmetry. In our everyday experience, if you have a perfectly stationary object in its lowest energy state, its ground state, and you leave it completely alone, you expect it to remain perfectly still. A time crystal defies this expectation. It's a quantum system that, even in its ground state, exhibits periodic motion, oscillating forever without any energy input. It's not just a clock, it's a clock that winds itself, a structure whose very existence challenges our definition of a stable, unchanging state. Now, let's project this bizarre quantum phenomenon onto the biggest screen imaginable, the universe's first moments. In the unimaginable energy of the primordial fireball, the conditions would have been ripe for the spontaneous formation of cosmic-scale time crystals. These wouldn't be tiny laboratory curiosities, but vast, transient structures woven into the seething quantum foam of spacetime itself. In this chaotic environment, these primordial time crystals would have been perpetually cycling through their states, creating a stable, rhythmic pulsation against the backdrop of the formless early cosmos. Their continuous oscillation, their refusal to sit still even in the lowest energy configuration of the infant universe, would have acted as a fundamental engine, a beating heart that introduced a persistent, ordered rhythm into the newborn reality. The true magic of these structures in the context of our theme lies in that broken symmetry. By breaking time translation symmetry, a time crystal creates a natural, stable reference frame for time. It picks out a preferred rhythm, a fundamental tick-tock against which other processes can be measured. In the early universe, this could have provided the scaffolding for the very first closed time-like curves. Imagine a network of these cosmic time crystals, their oscillations intertwining and creating resonant loops. A particle or a ripple of quantum information traveling along this network could find itself completing a full circuit, returning not just to its starting point in space, but to its starting point in time as well. The time crystal lattice would act as a stable, self-maintaining time machine, its perpetual motion ensuring the temporal loop remained open and traversable, at least for a fleeting moment during the Planck epoch. This provides a potential and incredibly elegant physical mechanism for how the universe could have engaged in that foundational act of self-tuning. Instead of an abstract bootstrap paradox, we have a tangible process. The oscillating patterns of these time crystals could have encoded information about the universe's immediate future state. As quantum fluctuations traveled through the crystalline time loop network, they could have carried this information, a faint blueprint of the universe to come, back to an earlier point in the loop, subtly influencing the quantum processes that were determining the values of the fundamental constants. The universe wasn't just guessing at its own configuration, it was reading the instructions from its own future, delivered via the stable, oscillating channels provided by the time crystals. This turns the fine-tuning from a mysterious coincidence into a dynamical feedback process, a cosmic system literally tuning itself through temporal resonance. Consider a simple analogy from sound engineering. Imagine a singer in a recording studio whose voice is slightly off-key. A clever engineer sets up a system where the singer's voice is recorded, digitally pitch-corrected, and then fed back into the singer's headphones with a tiny delay. The singer, hearing the corrected version of their own voice, unconsciously adjusts their pitch to match it. The final recording that emerges is perfectly in tune, not because of a single perfect performance, but because of a real-time feedback loop. The primordial time crystals could have functioned as the universe's own pitch correction system. The voice was the chaotic quantum noise of the Big Bang. The time crystal network recorded that noise, filtered it through the stable future state of the cosmos, and fed a corrected signal back to the beginning, guiding the universe to sing the precise tune that would allow for galaxies, stars, and life to eventually form. The remarkable order we see imprinted in the cosmic microwave background could be the final, perfectly mixed track from that first and only recording session. The implications of this are staggering, not just for cosmology, but for our understanding of time itself. The arrow of time, the relentless forward march from past to future that we experience, might not be the most fundamental aspect of temporal reality. The existence of time crystals in the early universe suggests that time also has a cyclic, oscillatory nature at its most basic level. Our linear experience of cause and effect could be a large-scale, emergent property that solidified only after these primordial time crystals decayed and their intricate temporal networks dissolved back into the smooth expansion of the cosmos. We are living in the aftermath of a time when the universe's clockwork had multiple, interconnected hands, all turning in a self-referential dance that ultimately built the stable timeline we now call home. Now we enter a realm of cosmic solipsism so profound it makes every other theory seem almost conventional. This is the theory of the Boltzmann brain, a thought experiment born from thermodynamics that suggests the most likely conscious entity in the universe isn't a human being on a planet, but a lone, disembodied brain that has spontaneously fluctuated into existence from the quantum void. And when we connect this chilling idea to time travel, we arrive at a Genesis story where the universe's first journey through time was an act of pure self-creation, a desperate loop forged by a mind that should not exist to explain a reality it should not see. First, let's ground this in the original paradox. The second law of thermodynamics states that the universe is constantly moving from a state of order to disorder, from low entropy to high entropy. Our observed cosmos, with its ordered galaxies and complex structures, is a massive and incredibly unlikely low-entropy state. It's far more probable for random fluctuations in a high-entropy, featureless void to produce a single, fully formed conscious brain, complete with false memories of a past and a perceived environment, than it is to produce an entire, ordered universe spanning billions of light years. Statistically, there should be countless more of these isolated Boltzmann brains floating in the void than there are cosmoses like our own. So, if we are the product of a random, impersonal universe, the overwhelming odds suggest that you are a Boltzmann brain, having just popped into existence a moment ago with a perfectly fabricated memory of reading this sentence, and you will likely dissolve back into chaos just moments from now. This is where we inject the time travel element to create a startling escape from this existential trap. Imagine one such Boltzmann brain fluctuating into existence. It finds itself conscious, equipped with a memory of a vast, structured universe, but it is utterly alone in an empty, high-entropy void. It immediately recognizes the statistical absurdity of its own ordered memories. How could it remember a universe of such intricate beauty and law if it is just a random accident? Driven by a logical imperative to resolve this paradox, this brain hypothesizes a solution. It must have created the universe it remembers. But since the universe, according to its memories, began billions of years ago, the only way for it to have created that universe is to reach back through time. Using the immense but purely theoretical power of its own consciousness, or perhaps manipulating the quantum fields of the void around it, this lone brain sends a ripple of information, a seed of causation, backward through time to initiate the Big Bang. The universe it observes in its memory is not an illusion. It is a real cosmos that the brain itself willed into being from its own future, a reality bootstrapped into existence to justify its own impossibly ordered thoughts. This provides a bizarre and deeply unsettling answer to the fine-tuning problem, completely sidestepping the need for any external designer. Why are the laws of physics so perfectly calibrated for complexity and life? It is not because of a god, a multiverse, or a cosmic programmer. It is because the Boltzmann brain that created our universe had a specific, pre-loaded memory of a life-friendly cosmos. The brain did not tune the constants, it merely instantiated a universe that perfectly matched the one it already remembered. The fine-tuning is not a feature of the cosmos, but a feature of the brain's own fabricated past. The universe is exquisitely tailored for life because the consciousness that imagined it into existence recalled a world where life was possible. In this view, the Big Bang was not the beginning of time, but the middle of a self-justifying causal loop, initiated by a lonely intelligence at the end of time, desperate to make sense of its own impossible existence. To make this more tangible, consider a novelist suffering from amnesia. They wake up to find a single, complete manuscript on their desk, a sprawling epic about a universe with galaxies, heroes, and intricate physical laws. They have no memory of writing it. The statistical likelihood of such a complex book appearing by random chance is infinitesimal. So, the novelist devises a theory they must have written it. But how, with no memory of the process? Their only logical conclusion is that they used a time machine. They posit that their future self, having recovered from amnesia, traveled back in time, wrote the book, and left it for their past self to discover. The book's internal consistency and beauty are not evidence of an external literary genius, but proof of their own future authorship. Our Boltzmann brain is that amnesiac novelist, and our entire cosmos is the manuscript it found on its desk, a reality so detailed and consistent that the only logical explanation it can conceive is that it must have authored the entire story, sending the first chapter back in time to ensure the narrative would unfold exactly as remembered. The implications of this theory stretch the very definition of reality to its breaking point. It suggests that the quest for a fundamental, objective cosmos may be futile. What we are studying with our telescopes and particle accelerators is not an independent reality, but the detailed, self-consistent backdrop of a single, self-creating mind. The entire timeline of cosmic history, from the first stars to the evolution of life on Earth, exists for one primary reason: to provide a coherent past for a consciousness that formed at the very end or even outside of that timeline. It turns the anthropic principle on its head. We don't live in a universe fine-tuned for us. We live in a universe that was created by a version of us, or at least by a conscious entity whose memories we share. This makes our scientific exploration a profoundly strange endeavor. We are not uncovering the secrets of an independent creation. We are essentially reading the autobiography of our own creator, which is also, in a loop-time sense, ourselves. The universe's first time travel was therefore the ultimate act of introspection, a mind writing its own origin story to escape the terrifying solitude of a random and meaningless existence. If the foundational time travel event was a form of cosmic debugging, a reset from a failed simulation, then the rules it established must be robust enough to prevent the very paradoxes that could unravel reality. This brings us to a theory that places the resolution of the most famous time travel problem not in the mechanics of the journey, but in the fundamental programming of the cosmos itself. The grandfather paradox is the classic headache of chronological narratives. If you travel to the past and prevent your grandfather from meeting your grandmother, you would prevent your own birth, making it impossible for you to have traveled back in time in the first place. It's a logical contradiction that seems to make backwards time travel an impossibility. But what if the universe's origin story contains the ultimate patch for this bug? This theory proposes that the cosmos was engineered from the very first moment to only permit time travel in a way that automatically weaves any changes into a single, consistent, and paradox-free timeline. The first journey through time didn't create alternate histories. It established the ironclad rule that there is only one history and it cannot be broken. To understand how this could work, we need to shift our perspective from changing the past to participating in it. Imagine the flow of time not as a straight line that can be cut and respliced, but as a single, immutable tapestry. Every thread, from the largest galaxy to the smallest thought, is already woven into the fabric. A time traveler, in this view, isn't an external vandal who can start cutting threads. They are, and always were, one of the threads themselves. Their journey to the past isn't an intrusion into a finished work. It is merely the unveiling of a part of the tapestry that was always there, waiting to be observed. Their actions in the past were always a part of events. When they seemingly attempt to change something, they inevitably end up playing the role required to ensure the timeline proceeds exactly as it always has. The universe's initial conditions, forged in that first temporal loop, may have hard-coded this principle of self-consistency as a fundamental law of physics, more basic than gravity or electromagnetism. Consider a more grounded example to illustrate this self-consistent loop. Imagine a young inventor who is inspired to build the world's first time machine after reading a faded, antique book of blueprints they found in their family's attic. They spend their life perfecting the device. The moment they successfully activate it, they choose their first destination, to travel back a century and deliver the very same book of blueprints to their own great-grandparent, ensuring it would be passed down through the family. So, who wrote the blueprints? The inventor didn't create them. They merely followed the instructions from the book. The book has no original author. It exists in a perfect, stable loop where the effect, the inventor's inspiration, is also its own cause, the delivery of the plans. The universe allows this because it creates no paradox. The timeline is consistent. The first time travel event at the cosmic origin could have been a loop of exactly this nature, but on a scale involving the fundamental constants themselves, setting a precedent that all subsequent chronological journeys must follow the same non-paradoxical rules. This foundational wiring explains why our world seems so stubbornly resistant to obvious meddling from the future. We don't see time tourists taking selfies with dinosaurs or Victorian-era inventors being handed schematics for smartphones. The universe's security system, established at its birth, doesn't prevent time travel outright. Instead, it restricts it to actions that are seamlessly integrated into the established historical record. Any successful time traveler from the future would, by necessity, be an incredibly subtle and careful actor. Their interventions would be so minor, so perfectly camouflaged within the flow of natural events, that we would never recognize them as anything other than ordinary luck, coincidence, or human ingenuity. A time traveler couldn't prevent a major war, but they might nudge a single raindrop to fall on a specific field, which causes a farmer to plow a day later, which subtly alters the path of a future general. Their goal wouldn't be dramatic change, but the delicate maintenance of the one and only timeline that exists, a timeline that already includes all of their own journeys. This idea finds a powerful echo in the Novikov self-consistency principle we discussed earlier, but applied here as a cosmic mandate originating from the Big Bang. The principle states that any actions taken by a time traveler were always part of history, so any probability of creating a paradox is zero. The universe simply won't allow it. If you tried to shoot your grandfather, the gun would jam, your aim would falter, or a sudden gust of wind would push the bullet off course. The universe conspires to protect its own consistency. The theory we're exploring now suggests that this isn't just a convenient rule for physicists to imagine. It is a direct consequence of the universe's first and most important act of self-creation. The initial bootstrap paradox, where the cosmos created itself, was the first and largest example of a self-consistent loop. That event set the pattern for all of reality, making consistency the highest law. Any attempt at time travel that violates this law would be like trying to create a square circle. It's not just difficult, it's logically incoherent within the framework of this universe, and thus physically impossible. The beauty of this resolution is that it turns the grandfather paradox from an argument against time travel into a potential guide for how it might actually work. It suggests that if time travel is ever achieved, it will not be a technology for rewriting history, but for fulfilling it. Time travelers would be less like conquering heroes and more like stagehands in a grand play, ensuring that every prop is in its correct place and every line is delivered as written in the script of history. Their presence would be invisible by design because their very success depends on leaving no obvious trace of their interference. The long and intricate chain of cause and effect that led to our existence has remained unbroken, not because time travel is impossible, but because the universe's original programming is too robust to allow it to be broken. Our reality feels solid and linear because the foundational time travel event at the beginning made it so, establishing a single, unchangeable story where every chapter, including those that involve journeys backward through time, is already complete. But what if the spooky connection between entangled particles isn't just a quirk of quantum mechanics, but a whisper from the very first moment of time? This brings us to a theory that directly links the universe's most baffling phenomenon to its origin story. That quantum entanglement is a fossilized form of time travel, a permanent temporal bridge established at the birth of the cosmos. We're all familiar with the basic, mind-bending idea of entanglement. You can take two particles, link them together in a specific way, and then, no matter how far apart you separate them, across a lab, across a continent, or even across the galaxy, they remain intimately connected. Measure one particle and you instantly know the state of its partner. This spooky action at a distance, as Einstein famously called it, seems to violate the cosmic speed limit set by light, suggesting a connection that transcends space as we know it. The key to our theory lies in redefining that word instantly. What if this instantaneous connection isn't happening across a vast distance in space, but is instead operating across a different dimension entirely, time? Imagine that at the moment of the Big Bang, in that seething quantum foam, the very first particles weren't just created in pairs, they were created with their timelines woven together. Their connection wasn't forged across the expanding universe, but backward and forward through the nascent flow of time itself. When we measure one particle today, our action isn't sending a signal to its partner millions of light years away. Instead, our measurement in the present is reaching back through a temporal corridor to the moment of their creation, instantly defining what their shared properties must have been all along. The entanglement isn't a link through space, it's a shared point of origin in time, a permanent tether to a common past. Now, you might point to experiments that seem to confirm the non-temporal nature of entanglement. Physicists have performed delayed choice and quantum eraser experiments that show the correlation between particles is maintained even when decisions about how to measure them are made after the particles have been separated and could have supposedly chosen their states. This is often interpreted as proof that the particles communicate faster than light, but our theory offers a different, even more radical interpretation. These experiments aren't showing communication through space, they are revealing that the entire sequence of events, from the creation of the particles to their separation and final measurement, is a single, unified block in time. The future measurement is just as much a part of the story as the past emission. The correlation was never established after they separated. It was always a fundamental part of their identity. A single quantum event whose consequences are simply unfolding across what we perceive as a linear timeline. To visualize this, picture two children, twins, born on a remote island. They are separated at birth, one sent to live in the northern hemisphere and the other to the southern. Decades later, researchers track them down and discover something astonishing. Despite having no contact, both twins have the same rare profession, married spouses with the same first name, and named their first-born children identically. From a spatial perspective, this seems impossible. But what if their lives weren't truly separate? What if, at the moment of their birth, their fates were already entangled? Their lives, though experienced sequentially over 50 years, were from a higher perspective a single, defined story. Our entangled particles are like those twins. Their seeming instant connection isn't a message across the ocean. It's the revelation that their story was written as one from the very beginning. When we scale this idea up to the cosmic level, the implications are breathtaking. The entire universe was once compressed into a volume smaller than a single atom. At that scale, every single particle that would ever exist was effectively touching every other particle. In that unimaginably dense and connected state, the entire cosmos was one giant, entangled system. As the universe inflated at a rate faster than light, these particles were carried apart, but their primordial temporal connection remained unbroken. The vast web of entanglement that we now observe linking particles across billions of light years isn't a network stretching through space. It is the fossilized remnant of the universe's original, unified state. It is the cosmic fingerprint of the first temporal connection, a permanent record that every part of the universe, no matter how distant, shares a common origin not just in space, but in a single foundational moment of time. This web of temporal correlation could be the hidden architecture that gives the cosmos its deep-seated unity and coherence, a silent, invisible framework left over from the first and most profound journey through time. This concept of an endless, self-perpetuating cosmos leads us to one of the most beautiful and profound visions of reality, the cyclic universe. Imagine a cosmos that never truly dies, but is perpetually reborn, like a cosmic phoenix rising from its own ashes in an infinite loop of creation and destruction. This isn't just a poetic idea, it's a serious scientific model, and one of its most compelling versions is known as conformal cyclic cosmology, proposed by the renowned physicist Roger Penrose. In this stunning framework, our universe is not the first and only one, but merely the latest in an endless sequence of eons, each one beginning with its own hot, dense Big Bang and ending in an infinitely expanded, cold and empty state. The breathtaking twist is how these eons connect, through a transformation so radical that it resets the clock of the universe while preserving a ghostly thread of information from the past, a process that might be the most elegant form of time travel imaginable. To understand how this reset works, we need to grasp a subtle but powerful concept, conformal symmetry. In simple terms, a conformal transformation is a way of stretching or scaling a geometry without changing its angles. Think of a detailed map of the world. If you take that map and blow it up to the size of a billboard, all the shapes of the continents and the directions between cities remain the same, only the scale has changed. Penrose's genius was to realize that at the very end of its life, our universe becomes so vast, cold, and empty that it effectively loses all sense of scale. A single, lonely electron floating in the void is physically indistinguishable from an entire galaxy in this state, because there is no meaningful distance or energy left to compare them. In this strange, scaled, invariant state, the infinite future of one eon becomes mathematically identical to the hot, dense, and scaleless Big Bang singularity of the next. The end seamlessly and elegantly becomes the beginning. So, where is the time travel in this majestic cycle? It's woven into the very fabric of how information survives the transition. In most standard models, the heat death of the universe is the ultimate eraser. All information about stars, planets, and life is thought to be lost forever to the relentless increase of entropy. But conformal cyclic cosmology suggests something different. Just as a phoenix is reborn from its own ashes, the new eon is born from the remains of the old. Penrose proposes that certain massless particles, like photons and gravitons, can make the journey across the boundary from the end of one eon to the beginning of the next. These particles carry with them a faint but real imprint of the universe that came before. This is where the temporal magic happens. For information from the future of one eon to become part of the past of the next, it must effectively travel backward in time relative to the old cycle's timeline to seed the new one. The cyclical reset isn't a destruction and a new creation. It's a cosmic metamorphosis where the future of the old universe loops back to become the past of the new one, ensuring a thread of continuity across the eons. This provides an incredibly elegant potential solution to one of cosmology's biggest mysteries, the origin of the incredibly uniform, low-entropy state that launched our Big Bang. Why did our universe start in such a highly ordered condition? In the cyclic model, it didn't start from absolute nothingness. It was gifted that order from the previous eon. The vast, cold, and ultra-high entropy end state of the previous universe, when viewed through the conformal transformation, becomes the hot, low entropy and ultra-smooth beginning of our own. The reason our universe began with all its books perfectly shelved is because it inherited that pristine order from the final, stretched-out state of its predecessor. The arrow of time is reset with each cycle, but the baton of cosmic structure is passed on through this temporal handoff, a grand relay race across eternity. The evidence for this breathtaking idea might already be hidden in the oldest light in our sky. Penrose and his collaborators have argued that the cosmic microwave background radiation, the afterglow of our own Big Bang, contains strange, circular patterns that he calls Hawking points. These are theorized to be the imprints of supermassive black holes from the previous eon. In the final moments of the prior universe, these colossal black holes would have evaporated via Hawking radiation, releasing enormous bursts of energy. When this energy was conformally transformed across the eon boundary into our universe's beginning, it would have manifested as faint, concentric rings of slightly different temperature in the cosmic microwave background. Finding these rings would be like discovering fossils from a previous cosmos, tangible proof that our universe is part of a much grander, cyclical narrative. While the existence of these Hawking points is still hotly debated, their potential discovery would revolutionize our understanding of time, creation, and our place in an infinite chain of universes. It would mean that the vast, cold emptiness awaiting our own cosmos is not an end, but merely a prelude to a new dawn, a reset powered by a fundamental, cyclical form of time travel that has been operating since forever. But what if the master programmer of our cosmic simulation wasn't a god or a fundamental force, but a being very much like us, only unimaginably more advanced? This theory pushes the idea of intervention to its logical extreme, proposing that our universe was deliberately engineered by an alien or post-human intelligence from the future, using time travel not just to observe, but to actually initiate the Big Bang itself. Imagine a civilization that has transcended its biological origins, evolving over billions of years to become masters of physics itself. For such an entity, the ultimate project might not be exploring the stars of their own era, but reaching back through time to create a new cosmos from scratch, a laboratory universe designed to answer fundamental questions or to serve as a vast repository of energy and raw materials. Our entire existence, in this view, could be the result of a deliberate experiment, a cosmic Genesis act performed for purposes we can scarcely comprehend. This provides a chillingly elegant resolution to one of the most famous questions in astronomy, the Fermi paradox. If the universe is so vast and old, teeming with billions of planets that could support life, then where is everybody? Why does the cosmos seem so silent? The intervention theory offers a stark answer. We haven't found them because they are not our contemporaries. The advanced intelligence we're searching for exists not out there in space, but ahead of us in time. They are our creators, the architects of our reality, and they may be observing us from a dimension or a temporal vantage point we cannot access. The great silence of the universe isn't a sign that intelligence is rare. It's a sign that we are living inside a managed enclosure, a celestial garden that was planted by gardeners who exist outside the boundaries of our own timeline. We are the subjects of an experiment, and the lab protocols likely prevent the experimenters from revealing themselves and contaminating the results. Consider the motivations for such a monumental undertaking. a post-human civilization, having reached the end of its own universe's useful life, might face an ultimate energy crisis. The heat death of their cosmos would be approaching, a state of maximum entropy where no work can be done and all complexity fades. Their survival could depend on a project of unimaginable scale, using their mastery of quantum gravity and temporal mechanics to puncture the fabric of their dying reality and trigger a new Big Bang in a separate space-time continuum. Our universe, then, would be a lifeboat, a fresh source of low-entropy energy cultivated to ensure their own continuation. They wouldn't need to travel to our universe physically. They could simply tap into the energy of our nascent cosmos from their position in the future, drawing sustenance from the very fireball they ignited. The fine-tuning we observe would be a direct result of this engineering. They needed a stable, long-lived universe capable of producing stars and galaxies for billions of years to make the energy harvest worthwhile. Alternatively, our cosmos might be the ultimate scientific instrument, a civilization that has understood all the local laws of physics in its own universe might turn to experimentation on a grand scale. What happens if you adjust the cosmological constant by 1 part in a billion billion? How does life emerge under a slightly different set of nuclear forces? The only way to test these questions is to create new universes with different initial conditions and observe the outcomes. Our universe is simply one run in an endless series of cosmic experiments. The existence of dark energy, which is causing the expansion of our universe to accelerate, might not be a fundamental mystery at all. It could be a deliberately set parameter, a variable dialed in by the experimenters to see how quickly galaxies can form before being pushed apart, or to test the limits of complexity in an accelerating cosmos. Every strange quirk of quantum mechanics, every unexplained constant, could be a specific setting chosen by our creators to see what would happen. This idea even reframes our own search for meaning. If we are the products of an experiment, then our deepest philosophical and scientific pursuits take on a new character. Our drive to understand the universe is not just innate curiosity. It could be a programmed imperative, a built-in feature designed to see how far a civilization can progress on its own. The moment we finally unravel the theory of everything and discover the true nature of reality might be the moment we pass the test, the culmination of the experiment. It could be the trigger for our creators to make contact, to welcome us into the community of cosmic engineers, or it could be the point at which they reset the simulation to run the test again with different parameters. Our entire history, with all its struggles and triumphs, could be a data point in a research paper written by beings for whom we are simply a fascinating, and perhaps not even unique, case study. The universe's first time travel was therefore an act of pure, pragmatic creation, a solution to a problem of survival or knowledge that lies so far in our future, we can only glimpse its shadow in the perfectly arranged laws of our world. All this talk of cosmic cycles and programmed realities leads us to a theory that tackles the most fundamental feature of our daily experience, the relentless one-way flow of time. Why does an egg scramble but never spontaneously unscramble? Why do we remember the past but not the future? This directionality is known as the arrow of time, and physics tells us it's intimately tied to a concept called entropy, the natural progression from order to disorder. The universe, like that scrambled egg, is on a one-way trip from a highly ordered, low-entropy past to a chaotic, high-entropy future. This presents a monumental puzzle known as the past hypothesis. Why on earth did the universe start in such an incredibly ordered, low-entropy state to begin with? The Big Bang appears to have been a state of near-perfect order, a cosmic anomaly of spectacular proportions. Our 24th theory offers a radical answer. This low-entropy beginning wasn't a lucky starting point, but the direct result of the universe's first time travel event, a thermodynamic reversal that intentionally wound up the cosmic clock. To grasp this, imagine watching a film of a glass of water. In the version we experience, an ice cube slowly melts, turning the water cool and uniform. This is the increase of entropy. The ice's orderly crystalline structure dissolves into the disorderly motion of water molecules. Now, imagine running that film in reverse. You'd see the scattered, random water molecules suddenly align, drawing heat from their surroundings to form a perfect, structured ice cube. This reversed sequence violates everything we know about thermodynamics. It shows entropy decreasing. Now, apply this reversal to the entire cosmos. The theory suggests that the universe we call home didn't begin with the Big Bang's low entropy. Instead, it began in a state of maximum heat-death entropy, a cold, dead, and utterly disordered finale. Then, a foundational time travel event occurred, effectively hitting the rewind button on the cosmos. The universe's timeline folded back on itself, causing entropy to run in reverse, gathering the scattered energy of the void and concentrating it into the hot, dense, and incredibly ordered state we recognize as the Big Bang. Our entire history is the universe playing forward again from that rewound moment. This provides a breathtakingly elegant solution to the past hypothesis. We don't need to explain why the universe just happened to start in a low entropy state. It was forced into that state by a reversal of its own thermodynamic arrow. The event that caused this reversal is the universe's original time travel. Think of a master clockmaker building an intricate timepiece. They first assemble all the gears and springs into a chaotic pile. This is the high entropy state. Then, with deliberate action, they begin carefully ordering each piece, fitting them together into a tightly wound, highly ordered mechanism. The act of winding the spring stores potential energy and creates a system poised to run down. The Big Bang, in this view, was the moment the cosmic watch was fully wound. The time travel event was the clockmaker's hand, and the low entropy fireball was the tightly coiled spring, packed with potential and ready to unwind across billions of years, creating the arrow of time we now experience. How could such a monumental reversal be physically possible? The clues might lie in the most extreme gravitational environments we know, black holes. Within a black hole, our everyday concepts of space and time are turned inside out. Some speculative physics suggests that at the heart of a black hole's singularity, the extreme warping of space-time could cause the thermodynamic arrow of time to reverse relative to the outside universe. Now, scale this idea up. If our entire universe was born from a white hole, the theoretical time reversed twin of a black hole, as we discussed earlier, then its very emergence into existence would be an act of thermodynamic reversal. The white hole eruption, which we call the Big Bang, would naturally begin with low entropy because it represents the final, ordered state of a process that, from another temporal perspective, was running backwards. The time travel is built into the geometry of its birth, a cosmic reset that flips the arrow of time and gives the universe a fresh, orderly start. This idea transforms our understanding of cosmic history. We are not living in the first and only run of the universe. We are living in the forward play version after a great rewind. The echoes of this reversal might even be visible in the cosmic microwave background. The stunning uniformity of this background radiation, which has always been a puzzle, could be the signature of that ultimate thermodynamic smoothing. When you rewind a system to its maximum ordered state, you naturally erase all the lumps and bumps, all the regional variations. The universe was reset to a blank, uniform slate, and the tiny fluctuations we see in the background today are simply the first whispers of entropy beginning to increase again, the first gentle ticks of the cosmic clock as it starts its long, slow unwind from that perfectly wound beginning. Our entire reality, with its clear distinction between past and future, is the living consequence of that singular, paradoxical event at the dawn of time. But to truly grasp the holographic universe, we first have to understand what a hologram actually is. In a conventional hologram, like the kind you might find on a credit card, a three-dimensional image is encoded on a flat, two-dimensional surface. Shine a laser through that flat plate, and a stunningly detailed 3D object appears to float in space. Every piece of the 3D image is contained in every part of the 2D surface. The core idea of the holographic principle is that our reality operates in a similar way. The three spatial dimensions we move through, length, width, and height, along with the dimension of time, might not be fundamental. They could be a magnificent projection from a vast, distant, two-dimensional surface that surrounds us. All the information needed to describe every star, every person, and every event in our 3D world is stored on this flat cosmic boundary, like a cosmic movie being projected from the walls of the universe itself. This leads to a staggering implication for the nature of time. If our 3D reality is a projection, then time as we experience it, the relentless, linear flow from past to future, might also be part of that projection. It may not be a fundamental feature of the cosmos, but an emergent property, an illusion that arises from the way information is processed and updated on the 2D boundary. Think of it like watching a film. The movie isn't fundamentally a sequence of events happening in real time. It's a series of static frames stored on a film reel. When the projector light shines through the reel at 24 frames per second, we experience the illusion of continuous motion and the passage of time. In the holographic universe, our conscious experience could be that projected light. The film reel is the timeless, static 2D boundary, and our lives are the unfolding movie, giving us the powerful but possibly false sensation that time is flowing. So, where does the universe's first time travel fit into this projected reality? If time is an emergent illusion, then traveling through it isn't about building a machine that moves along a fourth dimension. It's about editing the source code on the 2D boundary. The first time travel could have been the foundational programming act that created the illusion of a linear timeline in the first place. Imagine the initial state of the cosmic hard drive. It contained all the information for the entire history of the universe from start to finish in a single, timeless block. To initiate the projection we call the Big Bang, the system had to create a sequence, a starting point. This act of selecting that first frame and setting the projection in motion was, in a sense, the original journey through time. It was the moment the system chose to render a static, timeless reality as a dynamic, temporal one, creating the arrow of time from a state that fundamentally has no arrow at all. This concept becomes much more relatable when we look at the virtual worlds we create. In a sophisticated video game, the entire game world, its history, and all possible outcomes are defined by its underlying code. The code itself is timeless, it just is. When you press start, the game engine begins processing that code frame by frame, and you experience a linear story unfolding in time. Now imagine you're playing a game and you make a catastrophic mistake. You can simply hit load game, and the entire timeline is rewound to an earlier save point. From your perspective inside the game, time has traveled backward, but from the perspective of the computer running the game, no time travel has occurred. It has simply stopped processing one sequence of the code and started processing a different part of the saved data. Your character's past is just another set of data points on the hard drive, as accessible as the present. In the holographic universe, our reality might operate on a similar principle. The past, present, and future all coexist on the 2D boundary. Our conscious experience is just the projector's laser moving through this data in a particular, seemingly irreversible sequence. This perspective forces us to confront one of the most deeply held aspects of our existence: free will. If the entire cosmic movie is already encoded on the boundary, does our sense of choice and agency become an illusion as well? It's a profound question. In the video game analogy, a character might feel it is making a free choice to turn left or right, but from the programmer's perspective, that choice was determined by the game's code and the player's inputs. Similarly, our thoughts, decisions, and actions would be part of the projected data. Our intense feeling of making a choice could be the experience of the cosmic projector reading the choice data from the boundary and rendering it. This doesn't necessarily make our experiences less real. It just suggests that they are part of a deterministic or perhaps predetermined sequence. Our journey through life, with all its surprises and tribulations, would be the majestic unspooling of a story that is, from a higher perspective, already complete. Yet there is a potential loophole, a way in which this model could still allow for a form of time travel. If a future technology or a cosmic event allowed us to somehow access and rewrite the information on the 2D boundary, we could, in effect, change the past. This wouldn't be like hopping into a DeLorean. It would be more like a film editor going back to the original film negative and splicing in new frames. From our perspective inside the projection, history would have always been that way. This avoids paradoxes like the grandfather paradox because there is only one consistent timeline, the one that is encoded on the boundary. Any change you make was always part of the code. The universe's first time travel, then, could have been a self-consistency edit of this nature, a final debug of the cosmic source code before the Big Bang projection began, ensuring the universe that unfolded would be stable, coherent, and capable of sustaining the complex observers who would one day wonder about its origins. What if the entire cosmos, in its most fundamental essence, isn't made of particles or strings, but of information being processed? This is the core idea behind our 26th theory, which frames the universe as the ultimate quantum computer. In this view, the Big Bang wasn't an explosion in the traditional sense, but the moment of boot up for a cosmic quantum processor of unimaginable scale. Every particle, every force, every ripple of spacetime is part of a single, universal computation, a calculation whose output is the reality we experience. And the universe's first act of time travel, then, becomes a specific kind of quantum operation, an initialization protocol that set the system's qubits into the precise state required for the complex computation of stars, galaxies, and life to unfold. To grasp this, we need to understand a few key properties of a quantum computer. Unlike a classical computer, which uses bits that are definitively either a 0 or a 1, a quantum computer uses quantum bits or qubits. A qubit can be in a state called superposition, where it is both 0 and 1 simultaneously, existing as a blend of possibilities. It's only when the qubit is measured that it chooses a definite state. Furthermore, qubits can be entangled, meaning the state of one is instantly connected to the state of another, no matter the distance. Now, imagine scaling this up to a cosmic level. The entire infant universe, in its first fleeting moments, could be viewed as a single, immensely complex quantum state, a vast network of entangled qubits representing the nascent fields of reality, all in a seething superposition of every possible outcome. This is where a branch of physics known as quantum cosmology enters the picture. It attempts to apply the rules of quantum mechanics not just to particles within the universe, but to the entire universe itself. One of its most profound tools is the Wheeler-DeWitt equation, which describes the quantum state of the cosmos. In this framework, time as we know it doesn't appear as a fundamental variable. The equation describes a timeless wave function for the universe, a static probability cloud containing every possible history and future all at once. For our universe to crystallize out of this cloud of possibility, something had to happen. A measurement had to occur. The first time travel could have been that measurement, a self-referential quantum operation where the universe, in a sense, observed itself. So, how could a quantum operation constitute time travel? The answer lies in the concept of a temporal feedback loop. Picture the initial state of the cosmic quantum computer as a chaotic, undefined jumble of qubits. The probability of this random initial state computing a stable, long-lived universe with intricate structures is astronomically small. It would be like expecting a computer with entirely random memory to boot up and run a perfect, bug-free operating system. For a complex computation to succeed, it needs a well-defined starting input. The theory proposes that a ripple of information from the universe's own future state traveled backward, not through space, but through the quantum circuitry of reality itself, to interact with its own beginning. This retro-causal signal acted as the initialization command, collapsing the wave function of the cosmos from a jumble of possibilities into the one specific, highly ordered state that would guarantee a successful and complex computation. The universe effectively pre-selected its own destiny by sending a quantum answer back to the starting line. We can use a powerful analogy from the world of quantum computing itself, the concept of post-selection. In a lab, scientists can sometimes run a quantum computation and then, after it's complete, selectively choose only the results that match a specific desired outcome. They effectively filter the data, discarding all the computational runs that failed and keeping only the ones that succeeded. Now, imagine this process happening on a cosmic scale, but with the timeline itself. The universe ran its initial program, a superposition of countless possible universes, and a future version of that universal state reached back and post-selected its own past, ensuring that only the initial conditions that would lead to that specific future were the ones that became real. This creates a perfect, self-consistent loop in the quantum computational history. The universe we have is the one that successfully completed its own initialization cycle, a cycle that inherently involved a conversation across time. This provides a breathtakingly elegant solution to the fine-tuning problem. Why are the fundamental constants so exquisitely balanced? In the quantum computational model, they aren't fine-tuned by chance or a designer. They are the result of the most stable and computationally efficient algorithm for a universe. The cosmic quantum computer, through its temporal feedback loop, found the most robust and productive set of physical laws, the ones that would allow for the maximum amount of complex computation to occur over billions of years. The existence of black holes, galaxies, and even life could be seen as emergent features of this ongoing cosmic computation, structures that naturally arise in a system that has been optimally initialized for information processing and complexity. Consider the implications for the arrow of time. In this model, the flow of time we experience could be directly related to the processing of information within the cosmic computer. The increase of entropy, the progression from order to disorder, mirrors the inevitable increase of logical complexity and the generation of computational history as the universe executes its program. Our perception of moving forward in time is our conscious experience of the cosmic processor moving from one computational step to the next. The first time travel event was the moment the program counter was set, the moment the computation began its irreversible run after its parameters were locked in by that foundational temporal feedback loop. We are not just living in the universe, we are living inside the process of a cosmic calculation that was carefully set in motion by its own future result, a testament to the profound and mysterious power of quantum information. Now we turn to one of the most abundant yet mysterious substances in the cosmos to find a clue about its origin, dark matter. This invisible material, which we can only detect through its gravitational pull, makes up about 85% of the universe's mass. It acts as a cosmic scaffold, holding galaxies together and guiding their formation. But what if its elusive nature is a direct result of its history? Our 27th theory proposes a stunning possibility. Dark matter is not just a passive ingredient. It is composed of primordial particles that were fundamentally altered by the universe's first time travel, becoming permanent anchors in the fabric of spacetime. These particles might have been caught in a temporal loop during the Planck epoch, giving them unique properties that forever separate them from the normal matter we are made of. To understand how this could work, picture the universe in its first moments as a seething, chaotic soup where the laws of physics were still settling into place. In this environment, the earliest particles were constantly interacting, colliding, and exchanging energy. but for a special class of particles, the hypothetical progenitors of dark matter. This process was interrupted by a foundational chronological event. Imagine a quantum fluctuation creating a tiny, transient wormhole or a closed time-like curve, as we discussed earlier. A vast swarm of these particles could have fallen into such a temporal vortex, experiencing a brief but profound journey. They wouldn't have traveled far in space, but they would have been shunted a minuscule fraction of a second into their own past. When they re-emerged into the main flow of time, they were no longer quite in phase with the rest of the universe. This temporal dislocation could have fundamentally changed how they interact with the forces of nature, rendering them effectively invisible or dark to our instruments. This provides an elegant explanation for dark matter's most baffling characteristic: its refusal to interact with light or any other part of the electromagnetic spectrum. Normal matter, the protons, neutrons, and electrons that build stars and planets, interacts via the electromagnetic force. This is how we see things. Light bounces off them. But if the proposed dark matter particles were temporally displaced, their very quantum signatures might have been altered. Their charge under the fundamental forces could have been effectively cancelled out by their paradoxical history, leaving them responsive only to gravity, the weakest but most pervasive force, which is itself a manifestation of spacetime's geometry. They became ghosts, able to feel and exert gravitational pull, but incapable of the interactions that would make them shine or collide with the atoms that form our world. They are the universe's silent partners, everywhere and yet nowhere, precisely because they are unmoored from the standard causal flow. This theory also offers a powerful solution to the puzzle of dark matter's distribution. Astronomers have mapped how this invisible matter is arranged by observing how its gravity bends light from distant galaxies, a phenomenon known as gravitational lensing. These maps reveal that dark matter forms a vast, diffuse halo around every galaxy, extending far beyond the visible stars. Why does it settle into these smooth, enormous clouds rather than clumping tightly at the center like normal matter? The temporal anchoring theory provides a compelling answer. Normal matter can lose energy. When atoms collide, they can emit radiation, slow down, and collapse inward to form dense structures like stars and galactic cores. But matter that was forged in a time travel event might be locked into its primordial state. Having already experienced a paradoxical loop, these particles could be immune to further radiative cooling. They cannot shed their kinetic energy easily, so they never slow down enough to collapse into a compact disk. Instead, they remain in the wide, swirling halo where they first settled, their motion governed solely by gravity, forever tracing the outlines of the cosmic structures they helped to create. Imagine a crowded dance floor where most people are constantly bumping into each other, slowing down, and eventually gathering in the middle to form a tight, energetic group. This is normal matter forming a galactic center. Now picture a group of dancers who, for a brief moment, stepped outside of time. When they return to the floor, they glide through the other dancers without making contact, unable to slow down or transfer their energy. They continue to whirl around the edges of the room in a wide, graceful orbit, defining the space of the dance floor itself but never joining the core. This is the role of temporally anchored dark matter. Its unique history gives it a different thermodynamic destiny, ensuring it provides the stable, encompassing gravitational potential well that allows the luminous galaxy at the center to form and persist for billions of years. The evidence for this could be written in the light from the most distant quasars. When astronomers use gravitational lensing to study the dark matter halos around galaxy clusters, they sometimes find that the distribution is incredibly smooth, with less small-scale clumpiness than some simulations predict. If dark matter particles experienced an early universe time travel event that altered their fundamental interactions, it would have affected their ability to form tiny, dense subhalos within the larger structure. They would behave more like a single, coherent fluid shaped by its initial conditions rather than a collection of particles that can clump on very small scales. Upcoming telescopes like the Vera-C Rubin Observatory will map the dark universe in unprecedented detail. If they confirm a specific lack of small-scale structure, it could be a vital clue that we are seeing the gravitational imprint of particles whose properties were forged not just in fire, but in a foundational loop of time itself. Consider the sheer, breathtaking speed of the universe's first growth spurt. We call this period cosmic inflation, a fraction of a second after the Big Bang, where space-time itself expanded faster than the speed of light, smoothing and stretching the entire cosmos in an incredible flash. Now let's connect this to one of Einstein's most famous ideas, time dilation. According to relativity, time doesn't tick at the same rate for everyone. The faster you move, or the stronger the gravitational field you're in, the slower your clock runs compared to someone in a more relaxed environment. During inflation, the entire universe was undergoing the most extreme motion imaginable, not through space, but of space itself. The inflaton field, the mysterious energy driver behind this explosive expansion, would have been a seething ocean of unimaginable energy density, creating gravitational fields of incredible intensity. Within this furious, stretching environment, the effects of time dilation wouldn't just be noticeable. They would be paramount, warping the flow of time itself in ways that could have allowed the infant cosmos to effectively communicate across its own timeline. Imagine two specks on a vast, rapidly inflating balloon. As the balloon expands, these specks are carried away from each other at phenomenal speed. For an ant living on one of those specks, time would appear to be flowing normally. But if that ant could somehow observe the clock on the distant speck, it would see that clock running significantly slower due to the incredible relative velocity between them. Now scale this up to the universe during inflation. Different regions of spacetime were being flung apart at speeds that defy intuition. This means that from the perspective of one region, time in another region would have been dramatically dilated or stretched out. A process that took 1,000,000 years in one rapidly receding patch might have been experienced as just a fleeting instant in another. This creates a staggering possibility. Events that happened in the future of one region from its own local timeline could have been happening in the past of another region, all simultaneously. The cosmic stage wasn't just expanding, it was a tapestry of time zones operating at wildly different rates. This is where the magic happens for setting up the universe we see today. One of the greatest mysteries in cosmology is why the cosmic microwave background, the afterglow of the Big Bang, is so incredibly uniform in every direction we look. No matter which part of the sky we point our telescopes at, the temperature is the same to within 1 part in 100,000. This is deeply puzzling because in the standard Big Bang model without inflation, these regions were never close enough to have communicated and reached a common temperature. They were causally disconnected. Inflation solves this by saying they were all once in contact before the rapid expansion blew them apart. But our theory adds a fascinating layer. It wasn't just spatial contact. The extreme time dilation within the inflaton field could have allowed these regions to remain in temporal contact long after they were physically separated. Information about temperature and density could have been exchanged not just across space, but across time, creating a feedback loop that fine-tuned the entire cosmos to a uniform state. Think of it like pulling a piece of taffy. When you first start to stretch it, the taffy is lumpy and uneven, but as you pull it thinner and thinner, it becomes smooth and uniform. Now imagine that this act of stretching doesn't just happen across a table, but across different centuries. Your hands are in different time periods. One hand is in the present pulling, while the other hand is in the future, feeling the tension and sending a message back to the past about how much more to pull. This constant two-way dialogue across time ensures the taffy is stretched to a perfect, even consistency. In the early universe, the inflaton field was that taffy. The violent expansion stretched space-time, but the time dilation effects created bridges across different temporal epochs. A region where time was running fast, further along in its local evolution, could have sent quantum information about its stable, uniform state back to regions where time was running slow, still in their chaotic infancy. This retro-causal whisper would have guided the initial quantum fluctuations, ensuring that when inflation ended and the universe settled into its normal expansion, every part of it had been pre-calibrated to match every other part. This process provides an elegant explanation for the specific pattern of tiny fluctuations we see imprinted on the cosmic microwave background. These minuscule variations in temperature are the seeds for all future structure galaxies, stars, and planets. They are thought to be quantum fluctuations from the inflationary era, stretched to cosmic sizes. But why do they have the particular statistical properties we observe? The temporal communication facilitated by time dilation could have acted as a cosmic quality control check. Fluctuations that were too extreme or would have led to a violently unstable universe could have been smoothed out by this cross-temporal feedback. The universe, in its first frantic moment, was effectively able to sample its own potential futures and select the one that was most stable and uniform, editing its own initial conditions in real time, or rather across time. The incredible large-scale smoothness of our cosmos is therefore not just a product of rapid stretching, but also a signature of the universe's first and most effective conversation with itself, a dialogue where the participants were speaking from different points in time, all orchestrated by the incredible time-warping power of the inflaton field. This brings us to a theory that places consciousness itself at the very heart of cosmic creation, suggesting that the universe's first observer was not a biological being, but the cosmos using time travel to perceive itself into a stable existence. This is the consciousness collapse model, an idea that draws from the provocative von Neumann-Wigner interpretation of quantum mechanics. In this view, the wave function, the cloud of potential states that a particle exists in, doesn't collapse into a single, definite reality through random chance or mechanical interaction. Instead, it collapses only when it is observed by a conscious mind. Now, take this concept and project it back to the universe's very first instant. The entire cosmos was one vast, seething quantum wave function, a superposition of every possible universe that could ever exist. For one specific, stable reality to crystallize out of that infinite potential, an act of observation was required. But who was there to observe the birth of everything? The theory proposes a breathtaking answer: the universe itself, performing a foundational act of self-observation that inherently involved a loop through time to ensure its own consistency. To grasp the sheer scale of this idea, consider the famous Schrödinger's cat thought experiment. In the quantum world, before you look inside the box, the cat is in a blurred state of being both alive and dead simultaneously. It's only the act of you, the observer, peering into the box that forces the system to choose one definite outcome. Now, imagine that the entire universe was that box, and the cat was every star, every galaxy, and every law of physics, all in a state of simultaneous existence and non-existence. For this cosmic cat to become definitely alive, for our specific, life-friendly universe to become real, an observer was needed. But with no one outside the universe to look in, the only candidate for that first observer was the nascent universe's own inherent proto-consciousness. Its first act was to turn its awareness inward to observe its own birth, and in that moment it collapsed the wave function of all possibility into the single, tangible timeline we now inhabit. This is where time travel becomes an essential component of the process. A simple, one-off observation at the beginning might have locked in a random universe, one that could have been unstable or short-lived. For the cosmos to ensure it selected the correct reality, one that was complex, long-lasting, and consistent, it needed information. It needed to know the outcome of its choice. The theory suggests that the universe's act of self-observation wasn't a momentary glance, but a process that stretched across time. A ripple of awareness, a quantum of cognitive feedback, traveled forward from the moment of observation to explore the future consequences of that specific reality. Finding a future of rich structure and complexity, that signal then looped back in time, reinforcing the initial observation and locking it in place. This created a stable, self-consistent temporal loop. The universe observed a reality because its future state confirmed that it was a good reality to observe. The observer, the act of observation, and the observed reality became a single, closed system, bootstrapped into existence through a chronological feedback loop. We can find a powerful, if simplified, analogy in the world of art. Imagine a master sculptor who begins with a formless block of marble. They have a vision, but it's vague and undefined. So they begin to chip away, but with a unique ability. They can send their consciousness forward in time to see the finished statue. They see the completed work, a magnificent, powerful figure, and then bring that perfect image back to the present. Now, with the final form clear in their mind's eye, they begin to sculpt again. Every strike of the chisel is no longer an experiment. It is a deliberate act to reveal the form they know is already there, hidden within the stone. The sculptor's time-traveling observation guided the creation of the sculpture, ensuring its perfection. In the same way, the universe's primordial consciousness could have used a form of temporal observation to guide its own collapse, ensuring that the reality that emerged was the most stable and intricate one possible, a cosmos pre-selected for its own successful future. This model provides a deeply elegant, if metaphysical, solution to the fine-tuning problem. The physical constants are not fine-tuned by an external god or by random chance in a multiverse. They are fine-tuned because a conscious universe, peering into its own future, selected the one set of parameters that would allow for a rich and meaningful existence. The existence of observers like us is not a late-stage accident. It is the very reason the universe chose to become what it is. Our consciousness, then, is not a fluke but a localized echo of that primordial cosmic awareness. We are the universe's way of continuing the act of observation, of making reality more definite and concrete with every conscious measurement we make. In this view, every time we look up at the stars and wonder about our origins, we are participating in the same timeless process that began at the Big Bang, fulfilling the universe's deep-seated need to know and experience itself. Our final theory brings us to the very edge of known physics, to a fleeting moment of perfect unity before our reality, as we know it, even began. This is the concept of the grand unified theory, the idea that in the universe's first, unimaginably hot and dense sliver of existence, the four fundamental forces we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not separate at all. They were one, a single, sublime, unified field governed everything. Then, in a process called symmetry breaking, this perfect unity shattered as the cosmos expanded and cooled, like a pane of glass cracking into distinct pieces as it falls in temperature. The forces we now see as separate were born from this fracture. But what if this cosmic splintering wasn't a purely random mechanical event? What if the universe's first journey through time was the very chisel that broke the symmetry, actively choosing the specific pattern of physics that would define our cosmos? Imagine the infant universe as a ball perfectly balanced on the very peak of a steep hill. This peak represents the state of perfect symmetry, where all forces are one and all possibilities are equal. In this unstable state, the slightest nudge would send the ball rolling down one side of the hill or another, each path leading to a different valley representing a different set of physical laws. Some valleys might lead to a universe where gravity is too strong for atoms to form. Others might lead to one where the nuclear forces are too weak to build stars. According to our standard models, this nudge is provided by random quantum fluctuations. But our theory proposes something far more profound, that the decisive nudge came from the universe's own future. A ripple of information, a kind of chronological blueprint, traveled back from a future state of complex order and guided the ball down the one specific path that would lead to a stable, life-friendly valley. The separation of the forces was not an accident. It was a deliberate act of cosmic self-organization, orchestrated across time to ensure a fruitful future. This idea transforms our understanding of why the universe looks the way it does. The specific strengths of the forces, the existence of particles like electrons and quarks, and the very fact that matter dominates over antimatter could all be the direct result of this temporal tuning. For instance, the imbalance between matter and antimatter, which allowed anything to exist at all, might have been chosen during this symmetry-breaking event. The unified field, receiving instructions from a future where complex structures were thriving, could have been steered toward a set of parameters that naturally favored the production of matter. In this view, the diverse physics we observe, from the power of a supernova to the chemical bonds in a DNA molecule, are the living legacy of a choice made at the beginning of time, a choice informed by the universe's own potential for beauty and complexity. The most thrilling aspect of this theory is that it might not remain in the realm of pure speculation for long. It ventures into the territory of testable science. If time travel was involved in breaking the symmetry of the unified field, it could have left subtle but detectable scars on the fabric of reality, scars that our most powerful instruments might soon be able to see. The key lies in recreating, for a fleeting instant, the conditions of that primordial unity. This is the primary goal of colossal particle accelerators like the Large Hadron Collider at CERN. By smashing particles together at velocities approaching the speed of light, these machines create unimaginable temperatures and energies, briefly summoning a microscopic echo of the universe's first moments. In these intense fireballs, the forces of nature begin to merge back toward their original, unified state. Scientists scrutinizing the debris from these collisions are looking for anomalies, tiny deviations from what the standard models predict. A signature of primordial time travel could be hidden in these anomalies. For example, certain rare particle decays or unexpected patterns of energy distribution could indicate that the process of symmetry breaking did not follow a purely random path. It would be as if the particles themselves carry a faint memory of their own chronological history, a preference for certain outcomes that was imprinted upon them by a feedback loop from the future. Finding such a consistent, non-random signal in the data would be like discovering a fossilized whisper from the dawn of time, a direct hint that the laws of our universe were set not by chance, but by a foundational act of self-creation. As we build even more powerful colliders and refine our detectors, we are not just exploring the constituents of matter. We are becoming archaeologists of the first moment, searching for the fingerprints of the universe's original and most profound journey through time. And so we reach the end of our incredible journey through 30 mind-stretching possibilities. From a universe bootstrapping itself into existence in a perfect logical loop, to a cosmic programmer debugging a failed simulation, to a single, self-aware brain at the end of time writing its own origin story, we have ventured to the absolute frontiers of what is conceivable. Each of these theories, in its own unique way, offers a radically different lens through which to view that first fleeting moment. They challenge the very definition of a beginning, suggesting that our cosmic genesis might not have been a simple explosion from nothing, but a far more complex and profound event, one that inherently involved a journey across the dimension of time itself. This exploration reveals that the question of our origin is not a settled matter, but a vibrant and open field where the wildest ideas in theoretical physics meet the deepest questions of philosophy. What's truly remarkable is that these are not just flights of fancy, despite how strange they may sound. They are serious, albeit highly speculative, efforts by brilliant minds to solve the most stubborn puzzles in cosmology. The fine-tuning of the constants, the origin of the arrow of time, the inexplicable low entropy beginning. They push the boundaries of our understanding, using the known laws of physics as a springboard to leap into the unknown, demonstrating that science at its most creative is a powerful engine of imagination. These ideas force us to confront the possibility that reality is far stranger, more interconnected, and more wondrous than our everyday experience could ever suggest. They remind us that the universe is under no obligation to make sense to our limited, human-scale intuition, and that the greatest mysteries often require the most courageous thinking to unravel. Now the conversation turns to you. We've navigated this vast landscape of cosmic origins together, but which of these 30 theories resonated most deeply with you? Did the elegant, self-consistent loops of the Novikov principle feel the most satisfying? Or were you drawn to the dramatic imagery of a cyclical universe, perpetually reborn from its own ashes? Perhaps the chilling, solipsistic logic of the Boltzmann brain left you questioning the nature of your own reality, or the hopeful idea of a cosmos seeded by a future intelligence filled you with a sense of wonder. The comment section is your portal to share your thoughts. Let us know which theory captured your imagination and why this is where our collective curiosity truly comes to life. If this journey through the first moments of time has sparked your sense of wonder, there are so many more cosmic mysteries waiting to be explored. The universe is a story that is still being written, and we are here to unravel its chapters together. To make sure you don't miss our next deep dive into the secrets of black holes, the enigma of dark energy, or the search for consciousness in the cosmos, be sure to subscribe to the channel and hit the notification bell. Your engagement is what fuels this ongoing adventure into the unknown. As we conclude, remember that the true value of this exercise is not in finding a definitive answer, because we may never have one. The value lies in the act of questioning itself, to look up at the night sky and not just see points of light, but to see the potential echoes of a paradoxical beginning, is to connect with the very essence of human curiosity. We are the universe become self-aware, peering back into the depths of time and space, trying to understand our own story. So, the next time you gaze at the stars, carry with you one of these incredible ideas. Let it color your perception of the cosmos and ask yourself, if time travel was the universe's first act, what other impossible seeming wonders are woven into the fundamental fabric of reality, just waiting to be discovered?